Section 1.1 takes a look at exponent properties and how we can simplify complex exponential expressions. But first, before we start simplifying, we want to make sure we review what exactly those properties are that we saw in our previous math experience. To set these up, first I want to consider, let's look at a squared times a cubed. A squared times a cubed. A squared means there's two a's multiplied together, and a cubed means there's three a's multiplied together, which means total multiplied together we've got 5 a's. And what you'll notice there, and hopefully you remember from your algebra experiences, that when we've got two bases that are the same, a to the m times a to the n, what we want to do is we want to add those exponents together, m plus n. So this is our first exponential property, adding exponents from the same base. Now we can extend that a little bit with division. Let's take a to the fourth over a squared. Again, we'll recognize that as 4 a's in the numerator and 2 a's in the denominator, and what we'll see happen is when the a's divide out, we're just left with 2 of them, or a squared. This helps us recall the property that when we have a to the m divided by a to the n, what we will do is we will subtract those exponents. So our second property says with division, we subtract exponents. Third property that I want to remember is when we've got something like a cubed over a cubed. Now, if we use that subtraction system, if we subtract 3 minus 3, we get a to the 0 power. But to help us really understand what a to the 0 power is, let's simplify this the same way we simplified before, with 3 a's in the numerator and 3 a's in the denominator. We'll see that all those a's will divide out, and when everything divides out, the answer that we're left with is simply 1. This tells us the important property that any base to the 0 power is always equal to 1. Our next property we're going to look at is going to set up pretty similar to this. Property number 4, we're going to look at a squared over a to the 4th power. Now, if we use our subtraction rules, that'll give us a to the negative 2. But to really help us understand the significance of this negative exponent, we'll consider 2 a's in the numerator and 4 a's in the denominator. And we'll see when they divide out, what's left is a squared in the denominator and a placeholder of 1 in the numerator. This tells us that a negative exponent, a to the negative m, simply means we move it to the denominator, and we get a to the positive m. I want to notice that the negative exponent did not make the fraction negative. Negative exponents never make anything negative. Rather, the negative exponent simply moves it to the denominator as a positive exponent. Another property comes from if we have a cubed and then the whole thing is squared. A cubed means we have 3 a's, and squared means it appears twice, which means in total we have a to the 6th power. You'll recall the exponential property that says that if we've got a to the m power and all that is raised to the n power, we simply multiply those exponents together. So a power to a power, we multiply the exponents together. Number 6, if we've got ab cubed, that means the ab is going to appear 3 times. ab times ab times ab, which means altogether total there are 3 a's and 3 b's. This gives rise to the exponential property where if we've got a product raised to some power, we simply take each factor raised to that power. So ab to the m is a to the m, b to the m. Similar thing happens with division. If we've got a over b cubed, that means it's going to happen 3 times. A over b times a over b times a over b, which means total we've got a cubed in the numerator and b cubed in the denominator. So what we can do is use the exponent property that a over b to the m power simply means we take the numerator to that power and the denominator to that power. Our 8th property is going to be similar to this fraction power, a over b to the negative 2 power. The negative exponent we know is going to move things around. So the negative exponent's actually going to flip this over to b over a squared. And then we know the squared means we take the squared on top and the squared on the bottom. This gives rise to the exponential property that a over b to some negative exponent is going to flip the fraction over, making it b over a, and then we take the exponent of m as a positive exponent now on both of them. This becomes our 8th property. Our 9th property is one that we've seen before. If we had something like 8 to the 2/3 power, we would recognize that the denominator on the exponent becomes the index of a radical. And then we square what's left. The cube root of 8 is 2, and we still have the squared. 2 squared is 4. This reminds us of the property that the mth root of a to the n is simply a rational exponent, where n is on top and the index of m is in the denominator. And depending on the context, we might use this property backwards or forwards. We might start with the fractional exponent and change it to a radical, or we might start with a radical and change it to a fractional exponent. One last non-rule that I want to remind us of is if we have a plus b to the m. The common thing we see students do is they will say that's a to the m plus b to the m. But this is not correct. If we were to FOIL this out, you'll find that we have terms in the middle that have been lost by doing the shortcut. So there is no distributing of exponents on terms. And if you remember, terms are things that are added and subtracted. So if there's any adding or subtracting in there, there is definitely no distributing of those terms. Cannot do that. So that was a quick, less than 10-minute crash course review of the exponent properties that we've seen before. Let's take a look at actually simplifying some expressions using these properties. And we'll start simple and we'll build to more interesting problems. So let's start with 5x squared, y cubed, to be multiplied by 2x to the 4th, y to the 5th. We know when we're multiplying, we can add exponents together. First, starting with the numbers, though, 5 times 2 is 10. Then on the x's, we can add the exponents. X squared and x to the 4th is x to the 6th. And finally, on the y's, we can add the exponents as well. 3 plus 5 is 8. And so we have our final solution, 10x to the 6th, y to the 8th. How about this problem? If we have 9, a to the 6th, b to the 5th, c, and all that's raised to the 1/2. Because we have factors that are multiplied inside the parentheses, we can take the 1/2 and put it on each factor. So we have 9 to the 1/2 power. Notice I did not multiply 9 by 1/2. Exponent rules do not affect bases. Exponent rules affect exponents. So we have 9 to the 1/2. A to the 6th times 1/2 is 3. B to the 5 times 1/2 is 5/2. C to the 1 times 1/2 is 1/2 power. Oops, my 9 disappeared on me. I want to take a quick look at that 9 to the 1/2 power because we can actually simplify that. If you remember, 1/2 power would be a square root, a second root of 9. And the square root of 9 is 3, so we can rewrite this as 3a cubed, b to the 5/2, c to the 1/2 as our final solution. How about this one? If we have 3a squared over 25 cubed times 5a over 3 to the 5th power. To kind of help us out with these numbers, because the numbers are going to get huge, we're going to keep them in their factored form. So for example, the 25, I can factor that to 5 squared. So now when I take the 3 in, I'm going to treat that as 3 to the 3rd, a to the 3 times 2, and 5 to the 2 times 3. 3 to the 3rd, a to the 6th, over 5 to the 2 times 3 is 6th power. That is going to be multiplied by taking the 5 through onto each factor, 5 to the 5th power, a to the 5th power, over 3 to the 5th power. Now we can start to combine things together. First, let's look at the a's. A to the 6th and a to the 5th, we know we can add those exponents and get a to the 11th. On the 3's, we have 3 to the 3rd over 3 to the 5th. Subtracting those exponents, 3 minus 5 is negative 2. So the negative exponent tells me to put the 3 squared in the denominator. The negative moved it down into the denominator. 3 minus 5 giving us 2. Similarly with the 5's, we've got 5th power minus 6th power is 5 to the negative 1 power. The negative says move it down to the denominator. And so when we simplify, our numerator is a to the 11th. Our denominator is 5 times 3 squared, or 5 times 9, is 45. And we have our solution. Let's try this problem. Let's do x to the negative 2, y to the 5th, all that to the negative 3 power. Before we do any moving of variables, we have to take care of the parentheses, taking this negative 3 onto each part. That's going to give us x to the negative 2 times negative 3, positive 6th power, and y to the 5 times negative 3, negative 15th power. Now that we've taken care of the parentheses, now we can move that negative exponent to the denominator. So we have x to the 6th over y to the 15th for our final solution. Let's try another one. Let's do 7x cubed y to the negative 2 over 14x to the negative 4 y to the negative 3. This problem does not have any parentheses. Rather than subtracting with all the negatives, though, and risk a sign error, let's move all of these negative exponents around. So if there's a negative exponent, it's going to move to the opposite location. So the 7x cubed stays where it is. The y squared moves down. The 14 stays where it is. The x to the 4th moves up. And the y cubed moves up. Now as we're simplifying, 7 over 14 is going to reduce to a 2 in the denominator. For the x's, because they're on the same line, we can add those exponents. 3 plus 4 gives us x to the 7th. For the y's, being on different levels, we'll subtract them. 3 minus 2 gives 1y. And because it's positive, it stays in the numerator. We have our final answer. Let's try another one. Let's try a to the 5th over 32b to the negative 1/5 power. I like to do negative exponents outside of parentheses in 2 steps. One step, the negative flips it over, 32b over a to the 5th, all to the 1/5 power. Then on a second step, I'll take the 1/5 onto each part, giving us 32 to the 1/5 power, b to the 1/5 power, over a to the 5 times 1/5 is just 1. Now we'll remember the 32 to the 1/5 power, that's like saying the 32nd, or 32 to the 5th root. And if we factor 32 into 4 times 8, 4 is 2 times 2, 8 is 2 times 4, 4 is 2 times 2, we notice 32 has 5 2's in it. It's the 5th root of 2 to the 5th power, which means that's just going to be a 2, as the 5th power and the 5th root will undo each other, giving us 2b to the 1/5 all over a for our final solution. Let's do one more interesting exponent problem. Let's do 3a to the 1/3 plus b to the 1/3 times 9a to the 2/3 minus 3a to the 1/3 b to the 1/3 plus b to the 2/3. Because of all the adding and subtracting in this problem, we're not able to use our normal exponent rules. We can't just add exponents on a and b. We can't do any of those tricks. Instead, with the adding and subtracting in the middle, we're going to have to distribute everything through. First, we'll take 3a to the 1/3 times 9a to the 2/3. 3 times 9 is 27. And on the a's, we can add the exponent. 1/3 plus 2/3 is 3/3, or just first power. Continuing to distribute, we have 3 times 3 is negative 9. A to the 1/3 plus 1/3 is 2/3. B to the 1/3. Continuing to distribute onto the third term, we have plus 3, a to the 1/3, b to the 2/3. Now we'll distribute the b to the 1/3. When we multiply by 9, we get a positive 9, a to the 2/3, b to the 1/3. And then when we distribute onto the -3, we get -3 a to the 1/3. b to the 1/3 plus 1/3 is 2/3. And finally, plus b to the 1/3 plus 2/3. Whoops. Plus b to the 1/3 plus 2/3 is 3/3, or 1. When we try to combine like terms from this point, some interesting things happen. We've got -9 a to the 2/3 b to the 1/3. We also have a positive 9 a to the 2/3 b to the 1/3. We also have a 3 a to the 1/3 b to the 2/3, and a -3 a to the 1/3 b to the 2/3, which means all that's left on this problem is the 27a and the positive b for our final solution. Now, all these problems we've seen thus far, you might have seen on a pre-college math course in beginning intermediate algebra. We've done problems like this before. Now at the pre-calculus level, we want to take this to the next step. And that next step is we're going to start to see variables in the exponents. The properties are still the same. The rules are the same. The patterns are the same. There's just going to be variables along the way. So this shouldn't be a big jump to try and simplify things like a to the n times a to the 2n minus 5 times a to the 3n plus 1 squared. Same patterns as before, we have to take care of the parentheses first. And when the 2 goes through parentheses, it has to multiply by the entire exponent. So the first factor is staying the same, a to the n, a to the 2n minus 5. And on the third factor, when we multiply by 2, we now have 6n plus 2. Next, we know that if the bases are all the same, which they are, we can add the exponents on a. And when we add these exponents, we'll combine like terms. N plus 2n plus 6n is 9n. The other like terms of minus 5 plus 2 gives us a minus 3. And we have our final solution, a to the 9n minus 3. Same patterns, just variables in there that we get to simplify along the way. Let's try another example. Let's do 5b to the n plus 2 squared over b to the 3 times n minus 1 times b to the n over b to the n to the 5th power. Again, we need to take care of the exponents first by putting the squared onto each factor. So we have 5 squared, which is 25. B to the, we're going to multiply the entire exponent by 2. That's going to give us 2n plus 4. Over b to the, we might as well distribute, 3n minus 3 times b to the n over, again we multiply as we go through parentheses, b to the 5n. Simplifying a bit, let's go straight across. We've got several options, but I'm going to go straight across. We've got 25b to the 2n plus n, combining like terms, is 3n, and we still have a plus 4, over b to the 3n plus 5n is 8n minus 3. Then when we subtract exponents on the b, you'll see on the ends we've got 3n minus 8. That's going to be negative 5n. Hyperactive scroll. 3n minus 8n is negative 5n. And then 4 minus, be careful here, we're doing 4 minus negative 3. Minus a negative 3 makes it a positive. 4 plus 3 is 7. Be very careful of sign errors there. And to make this nicer, we don't like to see negative exponents, so I'm going to write this as b to the 7 minus 5n. Switching the order there so the first part of the exponent is positive, and then we can leave it like it is. So 25b to the 7 minus 5n. Let's try another example. Let's see if we can come up with a couple good ones here as we start to wrap up. We've got x to the m over y to the n squared times x to the 3m over y to the 2n to the negative 2 power, and then we're going to cube everything. So let's simplify from the inside out. Taking the 2 through onto both parts is going to give us x to the 2m, y to the 2n, times, taking the negative 2 through, we get x to the negative 6m over y to the negative 4n. All that's still cubed. But let's keep working on the inside. We can combine the x's and combine the y's by adding the exponents. 2 minus 6 is a negative 4m. Over y to the 2 minus 4 is negative 2n. And all of that is still cubed. We can do this at several points along the way. We might as well do it now. Take care of those negative exponents by moving them around, giving us y to the 2n on top and x to the 4m in the denominator. All of that is cubed. And so when we cube, don't want to lose my problem at the top, when we cube both parts, we get y to the 2 times 3, or 6n, over x to the 4 times 3, or 12m, and we have our final simplified solution. Let's try another. Let's do x to the 5n plus 1, y to the negative n plus 2, over x to the negative 3n plus 1, y to the 3n plus 2, and all of that to the 1 over 4n power. Let's start by simplifying our x's. When we do, we're going to subtract the exponents, 5n minus a negative 3n. Be careful there, we're subtracting a negative. 5 minus a negative is the same as saying 5 plus 3, which is 8n. And 1 minus 1 is 0. On the y's, if we start with the negative n and subtract 3n, negative 1 minus 3 is negative 4n. And 2 minus 2 is 0. And then we've got all that to the 1 over 4n. Let's go ahead and fix that negative exponent and move it down at this point. X to the 8n over y to the 4n, and all of that is to the 1 over 4n. When we take that exponent and put it on both parts, we get x to the 8n over 4n. Well, 8 over 4 is 2, and the n's will divide out, over y to the 4n over 4n, which is just 1. And so for our final answer on the exponents, we have x squared over y. Let's do another one with these fractional exponents in them. How about x to the 1 over 3n, x to the 1 over 6n, over x to the negative 1 over 2n, and all of that to the n over 2 power. This time I'm going to fix that negative exponent first. Let's get them all in the same line. X to the 1 over 3n, x to the 1 over 6n, x to the positive 1 over 2n, to the n over 2. One thing I'll notice is in order to add these exponents, we're going to need a common denominator. All the denominators have n, so we'll look at the 2, 6, and 3. Common denominator there is going to be 6. So we're going to multiply by 2 over 2, 1 over 1, and 3 over 3. And that's going to give us x to the 2 over 6n times x to the 1 over 6n times x to the 3 over 6n to the n over 2. Now we can add them together. 2 plus 1 plus 3 is 6. So we have x to the 6 over 6n, and if you divide out the 6's, we get 1 over n. But that is still to the n over 2 power. When we multiply those, the n's will divide out, and we're just left with x to the 1/2 power. Or we could change that to a radical if we wanted to as well. Both answers would be correct. The square root of x. Let's do one last problem as we wrap up these exponent properties. Let's say we've got x to the 3n plus 1, y to the 1 minus n, over x to the 2n plus 1, y to the n plus 1. And we're going to throw in a divide. And we're going to divide by x to the 3 times n minus 1, y to the negative 3, over x to the 3 times n plus 1, y to the 3 minus 3n. And we're going to take all of that to the n over 2 power. This is a great problem, mixing together lots of different exponent rules. Let's start with the first one and the x's. When we subtract exponents, because it's division, we get x to the 3n minus 2n is 1n, and 1 minus 1 is 0. For the y's, let's actually do it in a different color. For the y's, we're going to subtract those exponents. For the n's, we have negative n minus n is negative 2n. 1 minus 1 is 0. Divided by, what can we simplify on the right side? Well, if we distribute our 3's through, that would give us x to the 3n minus 3 over x to the 3n plus 3. For the y's, when we subtract those exponents, we'll just put them on top, keep them positive. Negative 3 minus 3 is negative 6 minus 3n. And all of that's still to the n over 2. So the right side is going to require a little bit more work. The left side's essentially done when we move the negative exponent. So we've got x to the n over y to the 2n divided by whatever we end up with on the right side. Let's look first at the x's. 3n minus 3n is 0. Negative 3 plus 3, I'm sorry, we're subtracting because of the division. Negative 3 minus 3 is negative 6. And then we still have the y to the negative 6 minus 3n. All of that still to the n over 2 power. Let's make those negative exponents positive. So we've got x to the n over y to the 2n divided by 1 over x to the 6th. And when we move the y down, we have to change both signs. This is very important that both signs change. Positive 6 and a positive 3n. All to the n over 2. Still simplifying on the right side because that n over 2 has to go on to each part. So the first fraction unchanged, x to the n over y to the 2n, divided by 1 to any power is 1, over x to the 6n over 2, that's going to be 3n. The n over 2 goes on the whole thing here. So that's going to be 6n over 2, which reduces to 3n, plus 3n times n over 2 is 3n squared over 2. Finally, how do we divide fractions? We multiply by the reciprocal. So we're going to multiply by x to the 3n, y to the 3n plus 3n squared over 2, all over 1. Now we can add the exponents on the x's. 1n plus 3n gives us x to the 4n. For the y's, we'll subtract the exponents. Subtracting 3n minus 2n gives us y to the n, plus that 3n squared over 2. And we have our final solution. We've got about 10 properties about exponents that we started with at the beginning. All 10 should have been a review of what we saw in previous math classes. Today what we're doing is reinforcing those concepts, practicing using those exponential properties with variables and the exponents on occasion. The homework set has several great examples that you need to practice working through, making sure that you master simplifying these exponents. Thank you for watching the video. In section 1.2, we're going to review everything we've seen about radical expressions and radical equations from our previous algebra experiences. First, a quick review of exactly what radicals are. Radicals. If some number to some exponent gives us some answer, then we say the nth root of that answer is the previous base. And an important subnote here is that we can only take even roots of non-negative numbers. We can take odd roots of anything, but even roots only with non-negative numbers. So for example, if we had the square root of 25, one might think of the square root of 25 as the square root of 5 squared. And because exponents and radicals are inverses of each other, we're just left with the base on the inside. So the solution becomes just 5. Similarly, we can do a higher root, maybe a cube root of 64. And what we're looking for there with the cube root is something to the fourth power is equal to 64. I'm sorry, not the fourth power, it's a third root. We're looking for something to the third power to equal 64. And you might recall that 4 to the third power equals 64, so the third root then must be that base of 4. Similarly, if we wanted the fourth root of something like 81, what we're looking for is the fourth root of 81, which is something to the fourth power. Well, 81 is 3 to the fourth power, so the fourth root then is just the base of 3. Now, a quick note about negatives. We already said that we have to be careful with negatives. If the index is odd, like the third root of -8, there really is no concern with the problem, because we can have a negative number as a base, -2 to the third power, under a third root. The answer is just a negative number, a -2. However, if the index is even, say we're just taking the square root of -9, we have no way to write this as the square root of something squared. Because whenever we square it, we'll always end up with a positive number. We'll never end up with that -9. So when the index is even and the radicand is negative, we say that it is not, well, we could say undefined, but I'm going to say non-real answer for now. We'll talk about non-real numbers in another video, but for now we'll just say we can't have a negative under a radical. Now these radicals were all nice because they simplified really quickly to the numbers we needed. However, simplifying radicals usually involves a little bit more. Sometimes we can't pull everything out of the radical like we had hoped. And so what we're going to do is we're going to consider the prime factorization of a number and then we can divide exponents by the index of the radical. So for example, if we wanted to take the square root of 50, several ways you can find the prime factorization. One way is to say 50 is 2 times 25 and 25 is 5 times 5. So the square root of 50 is going to be 2 times 5 squared. With square root, we know the index is 2, and so we can divide the 5 squared, divide that exponent by 2, and we get a single 5 coming out of the radical. The 2, there's no exponent on it. With no exponent, it's going to stay inside the radical. And so we will say the simplified form of the square root of 50 is 5 times the square root of 2. Similarly, if we've got the cube root of 16, we can factor 16 to 4 times 4 and 4 to 2 times 2, all the way down to prime numbers. So we say the cube root of 16 is the cube root of 2 to the fourth power. Now, when we take that exponent of 4 and divide by the index, we get a 1 with a remainder of 1. That 1 tells us a single 2 is going to move out, and the remainder of 1 tells us a single 2 remains inside the radical. Keep the index on the problem, and we have 2 times the cube root of 2. And we can extend this idea out into longer problems. Say we've got the fifth root of 64, a to the 5th, b to the 8th, c to the 12th. Well, first the 64 needs to be factored. 64 is 8 times 8, and 8 is 4 times 2, and 4 is 2 times 2. And so we'll see that factoring out. 64 has 1, 2, 3, 4, 5, 6 2's in it. So we'll say that's the fifth root of 2 to the 5th, a to the 5th, b to the 8th, c to the 12th. Now we can divide all of these exponents by the index. Oops, did I say 2 to the 5th? There's 6 of them, right? Should be 2 to the 6th. There we go. So now when we divide these exponents by the indexes, whatever is our whole answer comes outside of the radical, outside of the fifth root, and whatever remainders we have will remain inside the radical. So 2 to the 6th, 6 divided by 5 is 1, remainder 1. So 1, 2 comes out, and 1, 2 remains. A to the 5th, 5 divided by 5 is 1, remainder 0. So 1a comes out, and no a's remain. B to the 8th, 8 divided by 5 is 1, remainder 3. So 1b comes out, and 3 remain inside the radical. For the c, 12 divided by 5 is 2, remainder 2. So 2 come out, and 2 remain inside the radical. We have our simplified solution of 2abc squared times the fifth root of 2b cubed c. We can even play with this in multiplication. Say we've got the square root of 5a squared b cubed, and we multiply by the square root of 15ab to the 5th. When we combine these together, we'll want to make sure the numbers are factored. The 15 is 3 times 5, and the 5 is already 5. So under a single radical, we've got a 3 and a 5 squared. We've got a total of 4 a's and a total of 8 b's using our exponent properties from section 1.1. And now we look to see what we can pull out of the radical. The 3 remains behind because there's no exponent on it, but 5 squared means a single 5 can come out when we divide by the index of 2. A to the 4th. Boy, I really can't add today. 2 plus 1 is 3. That should be a to the 3rd. A to the 3rd. So we have 3 divided by 2 is 1, remainder 1. So 1 comes out, and 1 remains behind. On the b to the 8th, 8 divided by 2 is 4, remainder 0. So we have b to the 4th, and 0 remaining inside the radical. So when we're multiplying radicals, it's really nice because we can just combine the inside stuff. Dividing radicals gets a little bit more involved. First, I'm going to kind of introduce them with this simple problem. How about the square root? Let's do a cube root, a little more interesting, of 5 over 27. The way we take a radical of a fraction is we take the radical of both the numerator and the denominator. So we would have the third root of 5 over the third root of 27. Well, actually, I probably should have factored that 27 first. 5's already prime. And the 27 is 3 times 9 and 3 times 3, so we have 3 cubed. Cube root of 5 on top, in the numerator we can't do anything with it. But the cube root of 3 cubed, when we divide the exponent by the index, a single 3 comes out, and there's nothing left behind. So we have the cube root of 5 over 3. And this problem worked out all right because in our final answer there's no radicals in the denominator. In mathematics, we don't like to see radicals in our final denominator after we simplify them, which means on occasion we might have to do a little bit of work with this thing called rationalizing the denominator. Basically, we're saying we have this rule of no radicals in the denominator. The way we do this is we are going to multiply by any missing factors. On top and bottom, numerator and denominator, because we have to stay balanced. Here's what I mean by that. If we've got 3 over the 5th root of a squared, we don't like that 5th root in the denominator. So what we're going to do is we're going to multiply by a 5th root in both the numerator and denominator that has all the missing factors to get rid of the 5th root in the denominator. Notice our factor is a squared. We already have 2 a's, but we have a 5th root. To get rid of that 5th root, we need a total of 5 things. 5 a's. We already have 2 of them, so we need 3 more of these a's in both the numerator and denominator. When we do that, we've got a 3 outside the radical and a 5th root of a cubed in the numerator. So let's do that in a different color. 3 times the 5th root of a cubed. And then in the denominator, we've got 5 things under a 5th root, which means a single thing comes out, a single a. And for our final rationalized solution, we have 3 times the 5th root of a over a. Let's try another one. How about we do the 6th root of x cubed over y squared. Again, with fractions, we need to take the radical of both the top and the bottom, the numerator and the denominator. So we will do the 6th root of x cubed over the 6th root of y squared. Then we'll say for 6th root, how many more things do we need to clear the denominator? Well, right now it's y squared, so we need 4 more y's, y to the 4th, in both numerator and denominator. And because these are all under the radical, we can go ahead and multiply them together, x cubed y to the 4th. All over, we've got 6 things under a 6th root, a single y comes out, and we have our final solution. A square root problem becomes almost a simplified version of this, maybe the square root of 3/2. First, we need to take the radical of both the numerator and the denominator, root 3 over root 2. And with square roots, the index is 2. We've already got a single 2, we need a second 2. So we'll do square root of 2, numerator and denominator, to give us the square root of 6 over 2. So we've talked about how we can multiply and divide with radicals. Multiply, we can just combine the stuff. Divide, we want to make sure we take the radical of top and bottom if needed, and there's no radicals in the final solution. But what about how we add or subtract with radicals? Well, this is basically going through the exercise of combining like terms, or in this case we're going to call them like radicals. Just like if I had 5x plus 2x, we would pretty quickly say that was 7x by combining like terms. We can consider 5 times the square root of 3 plus 2 times the square root of 3. They both have a square root of 3 on them, which means we add the numbers in front 7, and we still have the square root of 3. Notice the radical part acts like a variable. And if it's a like term, we can combine it. So if we've got 8 times the 4th root of 5x plus 2 times the 4th root of 5x minus 7 times the 3rd root of 5x, we look for like terms in order to combine them. Well, you'll notice the 4th root of 5x is a like terms, but not the cube root. Cube root of 5x is close, but close only matters in horseshoe, scud missiles, and slow dancing, not in math. So as a result, we can only combine the like terms of 8 plus 2 to get 10 times the 4th root of 5x. And we still have negative 7 times the cube root of 5x. Combining a lot of these concepts together, we're now ready to simplify an expression such as the square root of 125 plus 17 times the square root of 1 over 5 minus 5/4, we'll make that to the negative 1/2 power, plus the 4th root of 25 over 16. There's a lot of pieces to this problem, and each piece simplifies differently. The 125 we can simplify by factoring it out to 25 times 5, and 25 is 5 times 5. So really the 125 is the square root of 5 cubed, and if we divide the exponent by the index, a 5 comes out, and left under the square root is a 5. The second term, 17 times the square root of 1/5, is taking the square root of the top and bottom, is 17 square root of 1 over the square root of 5. And we know we can rationalize the denominator by multiplying by the square root of 5 in top and bottom. This will give us 17 square root of 5 over the denominator of 5. The third term is 5/4 to the negative 1/2. We can use our exponent properties that we know that flips the fraction over 4/5. Keep the negative, well, we'll bring the negative down. So we got a plus between and then a negative. The 1/2 power means we are taking a square root of both parts. Well, the square root of 4 is 2 over the square root of 5. And then we can rationalize the denominator by multiplying by the square root of 5. So we have 2 square roots of 5 over 5. Finally, the 4th root of 25 over 16 becomes an interesting challenge. 25, when we factor it, is 5 times 5, 5 squared. 16, when we factor it, is 4 times 4, 2 times 2. So we have 5 squared over 2 to the 4th, and we want the 4th root of that. Well, when we take the 4th root of top and bottom, we have the 4th root of 5 squared over the 4th root of 2 to the 4th. Which is nice because, in the denominator at least, the 4th root of 2 to the 4th is clearly 2. But what about the 4th root of 5 squared? If we recall, we can write that index as an exponent. That's going to be 5 to the 2/4 power, where the index is the denominator, and we can reduce 2/4 to 1/2, or simply the square root of 5. Each term in this problem has a like term of the square root of 5. So as we start to combine things, 17 minus 2 is going to be 15 root 5 over 5, and that's going to reduce to 3 root 5. So we have 5 root 5 plus 3 root 5 plus root 5 over 2. 5 plus 3 is 8 root 5 plus root 5 over 2. Common denominator, so we can add them, is 16 root 5 over 2 plus root 5 over 2, gives us a final answer of 17 root 5 over 2. That is how we can add and subtract with radicals. Simplify each term, and then combine like terms. One last thing to talk about then with radicals is how we can actually solve radical equations. It's basically going to be a two-step process to take care of radicals. We need to get a radical alone, and then we can clear it with the opposite of a radical, which is an exponent. A reminder from our previous days in algebra is that we need to check answers in even radicals, because sometimes the answers won't work. So starting really simple, if we have the square root of 2x minus 3 equals 5, the way we solve this, the radical, you'll notice, is alone, is the opposite of a square root is a second power. We will square both sides so that second power and second root undo each other, leaving behind 2x minus 3 equals 5 squared, or 25. Add 3 to both sides to get 2x equals 28. And finally divide both sides by 2 to get x equals 14. Or so we think. Because the index was even, we need to check the answer to make sure it's correct. So going back to the original problem, before we did any squaring, that would be 2x, which we claim was 14, minus 3. We hope the answer is 5. Well, 2 times 14 is 28 minus 3, which we hope is still 5. And 28 minus 3 is 25, which we hope is still 5. And in fact, the square root of 25 is 5. So yes, our answer, x equals 14, is correct. Let's try another one. How about the square root of 5x plus 2 minus the square root of 3x minus 7 equals 0. This time we cannot just square both sides, because before we're allowed to square, we have to get one of the radicals alone by itself. It doesn't matter which one we solve for. Let's solve for the first one, just because it's already positive. Getting rid of the second one, we add the square root of 3x minus 7 to both sides. And that's going to give us the square root of 5x plus 2 equals the square root of 3x minus 7. And the way we get rid of square roots is we square both sides, because square and square root are inverses. Leaving behind 5x plus 2 equals 3x minus 7. Get the variable on one side by subtracting 3x. Get the numbers on one side by subtracting 2. And we're left with 2x equals negative 9. Finally, divide by 2 to find out that x is equal to negative 9 halves. Or so we think. We need to go back and check it in the original problem. The original problem was the square root of 5x, which we claim is negative 9 halves, plus 2, minus the square root of 3x, which we claim is negative 9 halves, minus 7, Hopefully that equals 0. Simplifying then, 5 times negative 9 gives us the square root of negative 45 over 2 plus 2 minus the square root of negative 3 times 9 is 27 over 2 minus 7. Getting common denominators of 2 under the radicals, negative 45 over 2 plus 4 over 2 minus the square root of negative 27 over 2 minus 14 over 2. And then we get the square root of negative 45 plus 4 is negative 41 over 2 minus the square root of negative 41 over 2. But we have a problem. Remember, we cannot take the square roots of negative numbers. This problem's not going to work out at all for us because we can't take the square root of negative numbers. This is a non-real result. We're going to cross off this solution altogether, at least until we talk about non-real answers. But for now we're going to say, gee, that didn't work out. We can't take the square root of a negative. No solution there. How about this problem? X equals the square root of 7x plus 51 minus 3. In this problem, again, before we get rid of the radical, we need to get the radical alone by getting rid of the other stuff. So we're going to add 3 to both sides, giving us x plus 3 equals the square root of 7x plus 51. Now we can get rid of the square root by squaring both sides. Squaring gets rid of the square root, and we're left with 7x plus 51. Be careful squaring the left side. The wrong answer is x squared plus 9. That was the rule that we went over yesterday. We need to FOIL this out. We square the first, x squared, and then x times 3 is 3x. 3 times x is 3x. 3 and 3 gives us 6x in the middle, plus 3 times 3 is 9. We can solve this equation. Because there's an x squared and an x, we need to set it equal to 0 and either factor or use the quadratic formula. So we'll subtract 7x and subtract 51. When we do, we get x squared minus x minus 42 equals 0. And that one does factor nicely. That's x minus 7, x plus 6 equals 0. So when we set each factor equal to 0, x minus 7 equals 0, x plus 6 equals 0, we get x equals 7, or negative 6. Or so we think. We need to check these answers back in the original problem. So first checking the 7. 7 hopefully equals the square root of 7 times 7 plus 51 minus 3. So we're still hoping the square root of 7 times 7 is 49 plus 51 minus 3. Still hoping the square root of 49 plus 51 is 100 minus 3. Still hoping the square root of 100 is 10 minus 3, and sure enough, we get the same thing on both sides. Our answer of 7 is correct. What about the negative 6, though? Turns out that with two answers, you could have one that works, two that works, or neither that work. So we do have to check this all the way down. So we'll go back and check again, this time with the negative 6. X is negative 6 equals the square root of 7x, or 7 times negative 6 plus 51 minus 3. 7 times 6 is 42, negative, plus 51 minus 3. Still hoping. We don't know this is equal. Negative 6 we hope is equal to negative 42 plus 51 is 9 minus 3. Still hoping the square root of 9 is 3 minus 3. But wait, 3 minus 3 is 0. This one did not work, so we have to throw out the negative 6, because negative 6 is not equal to 0. With radicals, we have to be very careful of those extraneous solutions that can get in the way. So the only answer that worked here, x equals 7. Let's try 1 equals the square root of negative 5 minus 3x minus x. Similar to last time, we need to get the radical alone before we take care of it, which means we need to get rid of the minus x by adding x to both sides. That gives us x plus 1 equals the square root of negative 5 minus 3x. Again, now that the radical is alone, we can solve by squaring both sides. Squaring gets rid of square root, leaving behind negative 5 minus 3x. And on the other side, x squared, 1x, and another x is 2x's, plus 1 squared is 1. Again, we're going to solve by getting the equation equal to 0, adding 5 to both sides and adding 3x to both sides. This gives us x squared plus 5x plus 6 equals 0. And that one factors quite nicely. But if you ever have problems with the factoring, don't hesitate to use the quadratic formula. This is x plus 2, x plus 3. And so when we set those equal to 0, x plus 2 equals 0, and x plus 3 equals 0, we're left with x equals negative 2 and negative 3 for our possible solutions. We don't know their solutions because we still have to check our work in the original problem. So we hope that 1 is equal to the square root of negative 5 minus 3 times, the first answer was negative 2, minus x, which we're saying is negative 2. So we hope the square root of negative 5, negative 3 times negative 2 is positive 6, minus the negative 2. And actually, I'm going to say add the opposite. We're going to make that plus 2. So we hope the square root of negative 5 plus 6 is 1, plus 2 equals 1. But you can see it coming now. The square root of 1 is 1 plus 2. 1 is not equal to 3. The answer of negative 2 does not work because when we plug it into the original equation, we find it was an extraneous solution. Let's try plugging the negative 3 in then. So 1, we hope, is equal to the square root of negative 5 minus 3x, which is negative 3, minus x, which is negative 3. Again, I'm going to add the opposite on the right side to make it plus 3. So we hope 1 is equal to the square root of negative 5, and negative 3 times 3 is positive 9, plus 3. So we hope the square root of negative 5 plus 9, or 4, plus 3 equals 1. But again, you can see it coming. 2 plus 3 certainly is not equal to 1. It is 5, so the negative 3 is thrown out as well. Turns out this problem also has no solution. Let's try one last problem to really get our brain thinking about how to work with these radicals. We're going to solve the square root of 4y plus 1 minus the square root of y minus 2 equals 3. Similar to the last problems we solved, we need to get one radical alone before we square both sides. So let's get the radical on the left alone, just because it's already positive. We're going to add the square root of y minus 2 to both sides. And this leaves us with the square root of 4y plus 1 equals 3 plus the square root of y minus 2. And now that that radical is alone, we can get rid of it by squaring both sides. Squaring a radical, we're left with 4y plus 1. On the right side, be careful we don't just say 9 plus y minus 2. This is a binomial with two parts to it, just like 3 plus x. This is 3 plus square root of y minus 2. The 3 squared is a 9. Then we multiply them together, giving us 3 square roots and 3 square roots, or a total of 6 square roots of y minus 2. Plus, when we square the last term, the square root goes away, leaving behind y minus 2. Let's combine the like terms to make this a little cleaner. So we have 4y plus 1 equals 9 minus 2 is 7. I'm also going to put the y next, plus y plus 6 square root of y minus 2. This might as well have been a problem that we solved earlier. Now we have a single square root that we need to get alone so that we can solve it. So we go back to what we did before. Subtract 7 and subtract y, just getting the radical alone. We have 3y minus 6 equals 6 square roots of y minus 2. Now because the 6 is multiplied by the radical, it's going to be okay to square at this point. So that's what I'm going to do, is I'm going to square both sides. The square is going to have to go on both parts, though. So we have to square the 6 to get 36, and we have to square the radical, leaving behind the inside stuff, the y minus 2. On the other side, we square in much the same way we always have. 3y squared is 9y squared. Multiplying, we have negative 18y, and negative 18y is negative 36y, plus 6 squared is 36. We've now reduced this down to something we've been solving for a long time now. Distribute the 36 through, we have 9y squared minus 36y plus 36 equals 36y minus 72. Then we get the variables on one side by subtracting 36y. Actually, we're going to make it equal to 0 because we want a factor. Add 72, and we get 9y squared minus 72y plus 108 equals 0. Now we can factor. Remember, with factoring, we always look for the GCF first, and this has a GCF of 9, which is really convenient, giving us y squared minus 8y plus 12 equals 0. And then continuing to factor, that's y minus 6, y minus 2 equals 0. And we set each factor equal to 0. The 9 doesn't have a variable in it. We don't care about that. Y minus 6 equals 0, y minus 2 equals 0, giving us two possible solutions of 6 and 2. Possible solutions, though, because we have to plug them back into the original problem to make sure they work. Let's start with the 6. Plugging 6 into the original problem, we get the square root of 4 times 6 minus 1, minus the square root of 6 minus 2, which we hope is equal to 3. Oh, I'm sorry, it's plus 1 inside the first radical. 4 times 6 is 24 plus 1 minus the square root of 6 minus 2, which we hope is equal to 3. 24 plus 1 is 25. 6 minus 2 is 4. We hope this is going to be equal to 3. And sure enough, the square root of 25 is 5. The square root of 4 is 2. It does equal 3. So our first answer of 6 is a good answer. We still have to test the 2, because sometimes both work, sometimes one works, and sometimes neither of them work. So this time testing the 2, we have the square root of 4 times 2 plus 1 minus the square root of 2 minus 2, we hope is equal to 3. Well, 4 times 2 is 8 plus 1 minus the square root of 2 minus 2 is 0. We hope this is equal to 3. 8 plus 1 is 9. Square root of 0 is 0. That's really boring. And you can see the square root of 9 is 3. It does, in fact, equal 3. That's a true statement. The answer of 2 also works. And so for this problem, we had 2 solutions. This video covered a lot of content. What radicals are, how to simplify radicals, how to multiply radicals, how to divide radicals or rationalize denominators. We talked about how to add and subtract radicals, and ultimately how to solve equations that have radicals in them. Take a look at the homework assignment in the book. We will see you in class. 1.3 Quadratic Expressions and Equations took a look at how we can work with expressions that have x squared in them and an x in them, and what we can do with them. And the big thing we're going to take a look at first is this idea of factoring. And just as a quick review of factoring, the first thing you should always do when factoring any problem is look for the greatest common factor first. And then after we get that greatest common factor out of there, then we can look at factoring what's left based on if it has 4 terms, or if it has 2 terms, or if it has 3 terms. Because if it has 4 terms, we're generally going to use, if you remember, a grouping strategy, where we group the left and right sides and hopefully find a binomial GCF in the middle. If there were 2 terms, we had several special products that we could use. Difference of squares, sum and difference of cubes, the special products would help us continue to factor. 3 terms are probably the most memorable, where we use kind of that guess and check method of finding the best factors for the trinomial that we're working with. So let's take a look at some of these examples. First, just basically looking at the GCF example, because we should always do the greatest common factor first. Always. Every problem. Don't forget the GCF first. So if we've got a problem like 7a to the 3n minus 28, what you'll see is both 7 and 28 are divisible by 7, so we can factor that 7 out. And when we divide the 7 out of each term, we're left with a to the 3n minus 4 for our factored solution. Similarly, if I look at an example such as 3x to the 5n plus 12x to the 2n, you'll notice both of those factors, 3 and 12, are divisible by 3. In addition, though, they have several x's in common. When we want to know how many x's in common, we take the smallest exponent out, and 2n is smaller than 5n, so we'll take out 2n. And when we divide 3x to the 5n by 3x to the 2n, we're left with x to the 3n. Plus, 12 divided by 3 is 4, and the x to the 2n's are divided out. And we have now factored out that greatest common factor. Let's try one more GCF problem. Let's do 5x to the 2n, y to the 6n, minus 10x to the n, y to the 7n, plus 15x to the 6n, y to the n. With three terms, we see all three numbers, 5, 10, and 15, are all divisible by 5. So we're going to start by factoring out a 5. We also look at the x's, and we see that every single term has an x on it. In fact, they all have at least n of them. N is the smallest exponent. And on the y's, we see they all have at least n of them also, taking the smallest exponent, the x to the n and the y to the n. And then what's left after we divide out 5x to the n, y to the n, is going to go inside the parentheses. 5 divided by 5 is 1. X to the 2n divided by x to the n is x to the 1n. Y to the 6 minus 1 leaves behind 5 n's. Minus 10 divided by 5 is 2. The x to the n divides out completely. We're left with y to the 6n. Plus 15 divided by 5 is 3. X to the 6 minus 1 leaves behind 5 n's, and the y to the n is completely divided out, and we have our solution. So always remember, with factoring, we will always do that GCF, greatest common factor, first before we do any other type of factoring. Once we've done that, though, we have to decide how many terms, I think we're on letter C, we have to decide how many terms are in the remaining expression. If there are 4 terms, we said we would use grouping, where we take the GCF out of the left and right sides. Again, as a reminder, we do this when there are 4 terms. And to kind of set up grouping, we're going to do a non-grouping example first, looking at x plus 3 times y minus 7 plus x plus 3 times y plus 2. And what we see in these two parts is both parts have an x plus 3 in common. That is the GCF, so we're going to factor it out as an x plus 3. Notice it did not come out as x plus 3 squared because there's 2 of them. Squared means we multiply them together. These are added together. These are factors that are pulled out. So we pull out a factor of x plus 3, leaving behind a y minus 7 plus a y plus 2. And we can simplify that last parentheses a bit by combining like terms. The x plus 3 is still there. We've got 2y's minus 9. Minus 7 plus 2 is 9. And we have now factored this expression. Now normally with grouping, though, we have to get it set up to be in that form that we want to work with. So we're normally going to have something like x squared y plus 2x squared minus 9y minus 18. And how grouping is going to work is we're going to split the expression in half with the 4 terms and factor the GCF out of the left and right sides. On the left side, we see a GCF of x squared, leaving behind y plus 2. On the right side, we see a GCF of negative 9, leaving behind y plus 2. And what makes this all work is that y plus 2 is a common factor on both. So we factor out that y plus 2, leaving behind the x squared minus 9. And this is a nice segue into our next topic because we're not done yet. X squared minus 9, you might remember, can factor further. we'll still have the y plus 2, but the x squared minus 9 is x plus 3 times x minus 3 to give us our final completely factored form. Let's look at that in more detail. That last step I did, the x squared minus 9, that is one of our special products that we talk about. Special products are generally what we look for when we have two terms. And there are two different types of special products, and the exponents are going to give away what we're talking about. The first type of special product is a difference of squares. A difference of squares is when we have something like a squared minus b squared, where we're subtracting two things that are squared. When we do subtract two things that are squared, it's going to come out to two binomials, where we take the square roots of both the first and the last, and one of them's a sum and one of them's a difference, and it doesn't matter which one. So plus or minus the square roots, basically. And it's really important for this to work, we need that minus sign. If it's a plus, you cannot factor it. But with a minus sign, you sure can factor it. So for example, if we had 36x to the 2n minus 25y to the 2n, we can take the square roots of both parts. The square root of 36 is 6, and the square root of x to the 2n is x to the n. Similarly, the square root of 25 is 5, and the square root of y to the 2n, square root divides the exponent by 2, is 5y. So when we factor to the n, 5y to the n, when we factor, it's going to factor to the sum and the difference of those square roots. So 6x to the n plus 5y to the n times 6x to the n minus 5y to the n. How about this one? Make it a little more interesting. We're going to say a plus 2 squared minus b plus 2 squared. Don't get thrown off by all the extra stuff. We are still subtracting two things that are squared. We are subtracting an a plus 2 and a b plus 2. So when it factors, it's going to factor to the sum and the difference of those square roots, a plus 2 and b plus 2. When we distribute the plus and minus through the parentheses, it'll even allow us to do a little simplifying. So we have a plus 2 plus b plus 2 after we distribute the plus. That's not going to change anything. We also have a plus 2. When we distribute the minus, it goes all the way through, minus b minus 2. And then when we combine like terms, we get a plus b plus 4 for the first factor, and a minus b for the second factor. And it is now completely factored. We can even do a combination of these two examples. We could do something like 16a to the 4th minus y plus 2x squared. Noticing the pattern and the structure of factoring here. We can take the square roots of both halves, and there's a minus in the middle. We can find the square root of 16 is 4. The square root of a to the 4th, dividing the exponent by 2, is a squared. The y plus 2x squared, the square root of that is simply y plus 2x in parentheses. And so to factor, we make it the sum and the difference of those square roots, 4a squared minus y plus 2x. And again, we'll simplify by distributing those negatives through and the positives through the parentheses. The positive's not going to do much excitement, so the first factor, 4a squared plus y plus 2x. The second factor, 4a squared minus y minus 2x. And we have our solution. So that's our first factoring special product. The second special product is not squares, but it is cubes. And we can do both sum and difference with cubes. You remember with squares it had to be a difference, it had to be subtraction. With cubes it can be either plus or minus, and both of them are really similar to each other. A cubed plus or minus b cubed is going to factor to a binomial and a trinomial. What I do is I take the cube roots of both parts. The cube roots of both parts are a and b. Then in the trinomial we square the first one, multiply them together, a, b, and square the last one. To fill in the signs, we do the same sign as the problem, the opposite sign of the problem, and then always plus. I think about the word soap. So the same sign will be either plus or minus. The opposite sign will be either minus or plus, because it's going to be opposite. And the last one's going to always be positive. Always plus. So if we are asked to factor something like 27a cubed minus 64b cubed, what's going to clue us into this formula is we see all the exponents are cubed. So we take the cube roots. What to the third power is 27? 3. The cube root of a cubed is a. What to the third power is 64? 4. The cube root of b to the cubed is 4b. The second part, the trinomial, we square the first, so 3a squared is 9a squared. Multiply them together. 3 times 4 is 12, ab. And then square the last term. 4 squared is 16b squared. Then we use SOAP to help us decide the signs. Because S means same sign as the problem, minus in this case. O means opposite, plus, and AP is always positive. We have now factored that difference of cubes. A sum of cubes follows the exact same pattern. If we had 8b to the 3n plus c to the 6n, we see those exponents are multiples of 3. That's going to clue us in on the formula for sum and difference of cubes. The cube root of 8 is 2. The cube root of b to the 3n, dividing the exponent by 3, leaves us just b to the n. The cube root of 6c to the 6n, divide the exponent by 3, leaves behind 2n. And then in the trinomial, we square the first. 2 squared is 4. B to the n squared is b to the 2n. Multiply them together, so we have 2b to the n, c to the 2n. And then we square the last one, which is c to the 4n, squaring, multiplying the exponent by 2. And then again, we think SOAP to help us with the signs. Same sign as the problem would be a plus, opposite sign minus, and then always plus for the last sign. We have now factored this difference of cubes. Sum of cubes. So with 4 terms, we use grouping. With 2 terms, we use the special products. With 3 terms, though, that's the one that gets the most attention. That is our guess and check method with 3 terms. And to set this up, we'll remember that we have a plus b times c plus d, and if we multiply it out, we would do A times C to get AC, A times D to get plus AD, B times C to get BC, and finally B times D to get BD. And kind of what makes it all work and come together as we're factoring is the first term times the first term equals the first term. First times first equals first. We're going to use that to help us guess what the first term should be in each factor. Similarly, you'll notice that B times D, the last times the last, equals the last term. We'll use that to guess what the last terms in each factor are, and then all we have to do is simply check. That was a bad bracket. We're going to check the middle part to make sure that it works. So if I have 6x squared plus 7x minus 20, and we're going to guess and check our way to the binomial factors that make this up, we would look first at the 6x squared. First times first has to equal first. What's a way we can multiply to 6x squared? Well, one guess might be 2x and 3x. Then the last term, negative 20, last times last has to equal 20. One guess might be 5 and 4. Then what I will do is I will check the middle stuff. And the way we check the middle stuff is we multiply the greens and pinks together, if you will. The outside, 2x times 4 is 8x. The inside, 5 times 3 is 15x. Can we use 8x and 15x to get the 7x in the middle? Positive 7x. We can if the 15x is positive and the 8x is negative. So we'll make the 8 negative and the 5 times 3, 15 positive. And we now have factored our expression. By the way, a nice little trick along the way is I knew not to do 4 and 5 because if I had put the 4 in the first factor, off to the side here, we had 2x and 3x. If I had put the 4 in the first factor and the 5 in the second factor, notice that would have given me a GCF of 2 in the first factor. We should never have a GCF inside a factor. So I knew right away that the 4 did not go with the 2 because they're both divisible by 2. The 4 had to go with the 3 because neither one had a common factor. They're only divisible by 1. So that helps me with my guess and check. Let's try a couple of these. Let's do negative 3x cubed plus 12x squared minus 9x. Looking at all three terms, we will notice they do have a GCF. Always do the GCF first. They both have a GCF of negative 3. Why negative? We like the first term to be positive, so we pull out a negative. All three terms also have an x on them, so we'll pull out an x. And we do that, that's left with a positive x squared, a negative 4x, and a positive 3. Now that we've got that GCF of negative 3x out front, now we can start talking about factoring what remains. X squared is probably x times x. 3 is probably 3 times 1. And so we check it on the outside. X times 1 is x. On the inside, 3 times x is 3x. Can we use x and 3x to get negative 4? Yes, if they're both negative. So we'll make them both negative. Negative 3 and negative 1. Notice a negative times a negative is a positive 3, like we want at the end. We have our solution. Let's do another one. How about 5x squared plus 30x plus 45? Again, the first thing we're going to look for is the GCF of 5. Leaves behind x squared plus 6x plus 9. Still with the 5 out front. X squared is probably x times x. 9 is probably 3 times 3. And if we check on the outside, there's 3x. On the inside, there's 3x. And if they're both positive, that'll give us 6x in the middle. And just by way of cleaning this up, you might notice both factors are exactly the same. Because they're the same, we're going to continue to factor them to 5 times x plus 3 squared for our final solution. One more. 15 minus 2x to the n minus x to the 2n. No GCF this time, so we'll go right to our factors. 15 is probably 5 times 3. And x to the 2n, notice if you divide that exponent by 2, you get x to the n times x to the n. Multiplying the outside, we have 5x to the n. Multiplying the inside, we have 3x to the n. We want to end up with negative 2. The way we get negative 2 is we make the 5 negative. So the factor with the 5 was on the outside, negative on the outside, so 5 times negative x to the n is negative 5x to the n. And a positive 3x to the n on the inside. We have now factored our trinomial. So that's the first half with these quadratic expressions and equations. Factoring. GCF first. 2 terms, we use a product, special product. 3 terms, guess and check. 4 terms, we'll use grouping. That's how we factor. And now that we know how to manipulate these equations, I think I'm on F, we're ready to actually solve these equations. And there are actually 4 ways that we go about solving these quadratic expressions, these quadratic equations, I'm sorry. The first way, the most common way, is when possible, we'll use the zero product rule. And the idea of the zero product rule is if 2 things multiplied together equal 0, then one of them has to equal 0. Then A equals 0 or B equals 0. In other words, if we can set it equal to 0 and factor, we can set each factor equal to 0. So if I have 2x cubed minus 2x squared minus 4x equals 0, and we want to know our possibilities for x, first thing we always look for when factoring is the GCF. You'll notice all factors are divisible by 2 and x. That leaves behind x squared minus x minus 2 equal to 0. Continuing to factor the remaining trinomial, we get x minus 2 and x plus 1 using guess and check. Now that it's factored, we've got 3 individual products that equal 0. One of those products then must be 0. So we say either 2x equals 0, x minus 2 equals 0, or x plus 1 equals 0. Solving each of these by dividing by 2, x equals 0, adding 2, x equals 2, and subtracting 1, x equals -1, we get our three possible solutions for this problem. Let's do another example. Let's do 3x squared plus x equals 2. One thing that we notice is different about this problem is not equal to 0. It's equal to 2. Whenever we're solving an equation that has both x squared and x in it, we need the equation to equal 0 before we can move on. So we'll make it equal to 0 by subtracting 2. That leaves behind 3x squared plus x minus 2 equals 0. And now we can solve by factoring. 3 terms, so we'll use guess and check. 3x squared is probably 3x times x. 2 is probably 2 times 1. And so when we check that on the outside, 3x times 1 is 3x. On the inside, 2 times x is 2x. So if the 2x is negative, the middle part negative, the outside part positive, we would get the 1x in the middle that we want. And then, now that it's factored, we can set each factor equal to 0. 3x minus 2 equals 0, and x plus 1 equals 0. These all solve really quick. The first one we add 2 and divide by 3 to get 2/3. The second one we subtract 1 and we get our second answer of -1. Let's try another problem. This problem is one of the easiest problems. 4x squared equals 8x, and it's probably one of the most missed problems because students want to do things like divide by x. We can never divide by a variable because we can never divide by 0, and we don't know if the variable is equal to 0. So we can't divide both sides by a variable. Again, like the last problem, notice we have x squared and x. The way we solve those is we make them equal to 0 by subtracting 8x from both sides, giving us 4x squared minus 8x equals 0. Factoring, first thing we look for is GCFs, and there's a GCF of 4x, leaving behind x minus 2 equals 0. Once it's factored, we set each factor equal to 0. 4x equals 0, and x minus 2 equals 0. Adding both sides by 4, our first answer is 0. Adding 2 to both sides, our second answer is 2. The reason we couldn't divide by x here is that indeed it turned out that we were dividing by x equals 0, and we can't divide by 0. Whenever there's x squared and x, make the equation equal to 0 and factor. Let's do one last. 25x squared equals 30x minus 9. Again, we want the equation to equal 0. We like x squared to be positive, so let's subtract 30x and add 9 to both sides, keeping the x squared positive, giving us 25x squared minus 30x plus 9 equals 0. Factoring then, 25x squared is probably 5x and 5x. 9 is probably 3 and 3. And if they're both negative, you see we've got 5x minus 3, and 5x minus 3 is going to give us 15x, and 15x is 30x in the middle. Since both factors are the same, we'll write it as 5x minus 3 squared equals 0, which means there's really only one factor that we have to make equal to 0. Solving this equation, we would add 3 and divide by 5. So x is equal to 3/5. And in this problem, we only ended up with one solution of x equals 3/5. So if there's an x squared and an x in the problem, we're probably going to make it equal to 0 and factor. But there's a few other ways we can attack the problem. One way is to extract a square root. we're going to do this when there is no x term, just an x squared term. And what we're going to do is simply get rid of the squared by taking the square root of both sides. So for example, if we have 3x squared equals 18. Before we take the square root of both sides to get rid of that x squared, let's get the squared part alone by dividing both sides by 3, giving us x squared equals 6. Then we can take the square root of both sides, because square and square root are inverses, leaving x equals plus or minus the square root of 6. Which brings up an important point. When we take the square root of both sides, we must have a plus or minus in our solution, because squares have two solutions. Square root needs to give us both the positive and the negative potential solution. So if we have x plus 3 squared equals 5, again, notice we can take the square root of both sides to clear the squared. Leaves us with x plus 3 equals plus or minus the square root of 5. We're not done yet, though, because x is not alone. We still need to subtract 3 from both sides. So we get x is equal to negative 3 plus or minus the square root of 5. And this becomes our final solution. Extracting square roots leads to the completing the square, which we'll get into more detail in a future lesson. Completing the square, though, leads to, you might remember, everybody's favorite formula from pre-college math, the quadratic formula. Which you should have memorized. If you don't have it memorized yet, memorize it now. X is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. This is an important formula for you to have memorized in this class and your future math classes as well. The nice part about the quadratic formula is every problem simplifies the exact same way. So we only need to do one example. Let's do 2x squared plus 5x minus 11 equals 0. Again, it has to equal 0, and the advantage of the quadratic formula is we're going to use it when we can't factor. If we were to try to factor this, we would find nothing that worked, that gave us that 5 in the middle. Feels like a dead end until we use the quadratic formula. 2 is a, 5 is b, negative 11 is c, so x is equal to the opposite of b, negative 5, plus or minus the square root of b squared, 5 squared, minus 4a, which is 2, c, which is negative 11, all over 2a, which is 2. And then we simplify. 5 squared is 25. Notice the two negatives. A negative times a negative is going to make a positive. 4 times 2 is 8, times 11 is 88, over 2 times 2 is 4. So x is equal to negative 5 plus or minus the square root of 88 plus 25 is 113 over 4. And that is our final solution. So those are kind of the ways we can solve an equation, by either factoring, extracting the square root, or the quadratic formula. I want to look at one other type of problem, though, that's going to become very important to us in this class, is when a problem is quadratic in form. So if you've been spacing out up till this point because it feels like review, time to wake up. This is the important new stuff that builds on this review. we're going to have stuff that's quadratic in form, and the trick is we want you to see the stuff as the variable. So to set up a simple example first, if we've got x to the 4th minus 26x squared plus 25 equals 0. Notice the x squared is in the middle instead of a regular x. If we think about the x fourth as x squared squared, we've got stuff squared minus 26 times stuff plus 25 equals 0. Well, we can factor this. X to the 4th is probably x squared times x squared. 25 is probably 5 times 5, but when we test that out, what we'll find is that's going to give us 10 in the middle, not 26. So we need a different guess. The only other way to get 25 is 25 times 1. And if they're both negative, that will give us negative 26x squared in the middle. But this actually factors further. X squared minus 25 is a difference of squares. X plus 5, x minus 5. And x squared minus 1 is also a difference of squared. X plus 1, x minus 1. So now we can set each factor equal to 0. X plus 5 equals 0, x minus 5 equals 0, x plus 1 equals 0, x minus 1 equals 0. And solve each equations to get solutions of negative 5, 5, negative 1, and 1. That one we probably could have done before, though, just stretching that x to the 4th is x squared times x squared. Let's try a more interesting problem. Let's do 6x to the 2/3 minus 5x to the 1/3 minus 4 equals 0. We can still factor this. X to the 2/3 can be split into two parts, x to the 1/3 and x to the 1/3. So 6 is probably 2x to the 1/3 times 3x to the 1/3. 4 could be 2 and 2, but if we did 2 and 2, we would have a GCF in the left factor, so 2 and 2 is not going to work. So it's probably 4 and 1, and the 4 can't go with the 2, so I'm going to go 4 and 1 on the outside. See what that gives me. 2 times 4 is 8x to the 1/3. 3 times 1 is 3x to the 1/3. If the 8 was negative, negative 8 plus 3 would be that negative 5. So I'm going to make the 8 negative. That was the 2 times 4. Let's go ahead and make it blue. And the 1 positive. Now we can set each factor equal to 0. 2x to the 1/3 plus 1 equals 0. And 3x to the 1/3 minus 4 equals 0. Solving the first one, we get x to the 1/3 equals negative 1/2. The way we get rid of a 1/3 is we do the reciprocal exponent, the third power. So x is equal to negative 1 cubed is negative 1, over 2 cubed is 8. Our first answer is x equals negative 1/8. The second answer, for the x to the 1/3, we will add 4 and divide by 3. And then we get rid of the 1/3 power with the reciprocal 3 power. And so x is equal to 4 cubed is 64, over 3 cubed is 27. And we have our next solution. Let's look at some more interesting problems. How about x plus 1 over x plus 3 squared plus x plus 1 over x plus 3 equals 6. What we're going to do is we're going to treat the stuff as its one ugly looking variable. That stuff is going to stay together. First, though, it has to equal 0. So we'll subtract 6 from both sides. X plus 1 over x plus 3 squared plus x plus 1 over x plus 3 minus 6 equals 0. To factor it, then, the stuff squared is probably the stuff times the stuff. X plus 1 over x plus 3 times x plus 1 over x plus 3. The negative 6 is probably 2 times 3. And if we make the 3 positive and the 2 negative, that'll give us 1 stuff in the middle. So we make each factor equal to 0. X plus 1 over x plus 3 minus 2 equals 0. And the stuff, x plus 1 over x plus 3 plus 3 equals 0. Solving is going to take a little bit more work here, but we can do that. Add 2 to the first one to get x plus 1 over x plus 3 equals 2. And now that the fraction is alone, we can clear the fraction by multiplying both sides by x plus 3. Leaving behind x plus 1 equals, distribute the 2, 2x plus 6. Subtract x from both sides and subtract 6 from both sides, we get negative 5 equals 1x for our first solution. Second equation, solving the exact same way. This time we're going to subtract 3 equals to a negative 3. And then we can multiply both sides by the denominator of x plus 3, because that denominator will divide out, leaving x plus 1 equals, distributing the negative 3, negative 3x minus 9. Now we add 3x to both sides, subtract 1, getting all 4 x's on one side and negative 10 on the other side. And when we divide by 4, x is equal to negative 5 halves for our second solution. So if we can recognize the problem as being quadratic in form, treating the stuff as the variable, it can factor and solve just like all the other stuff we've seen. So the homework assignment in the textbook takes a look at factoring, takes a look at solving by either zero product rule, extracting square roots, quadratic formula, possibly quadratic in form. Take a look at it, give it a good practice, and we will see you in class. Section 1.4 of our textbook reviews how we simplify rational expressions, specifically when we're multiplying and dividing them, and specifically dividing complex fractions. So let's first start with how we can reduce rational expressions simply by dividing out factors. I want to notice that we divide out factors, things that are multiplied. We will never cancel terms, things that are added together. If things are added together, we cannot reduce the fractions. We can only divide things that are multiplied together. So if we have something like x squared plus x minus 90 over x squared plus 13x plus 30, and it's multiplied by x squared minus 9 over x squared minus 81, we cannot do any reducing because of all that adding and subtracting in there until we first factor everything. So let's factor that first fraction, that numerator. X squared is going to be x times x, and 90 is 9 times 10. If the 10's positive and the 9's negative, we get positive 1 in the middle. In the denominator, we've got x times x to be x squared. And 30 is going to come from 10 and 13. I'm sorry, 10 and 3, with both of them being positive. Then we have a times. X squared minus 9, that's a difference of squares. That's x plus 3, x minus 3. And the denominator, x squared minus 81, that's also a difference of squares. X plus 9, x minus 9. And now that it's factored, now we can divide out factors that appear both in the numerator and denominator. The x minus 9 goes out with the x minus 9. The x plus 10 goes out with the x plus 10. The x plus 3 goes out with the x plus 3. And all that we have left in the numerator is an x minus 3. And in the denominator, an x plus 9 for our simplified expression. When we are multiplying, we can just start reducing out common factors. When we're dividing, there's one extra step we're going to take. So let's take a look at that with 3x squared minus 4x minus 15 over 3x squared minus 14x plus 15 divided by 3x squared minus x minus 10 over x squared minus 4. Because this problem is dividing, we recall that with fractions, the way we divide with fractions is we multiply by the reciprocal. So as we factor, we're going to flip this fraction upside down. First, though, the first fraction, let's factor it. In the numerator, 3x squared is 3x times x. 15 is 5 times 3, and the 3 is not going to be with the other 3. And if the 3 times 3, 9 is negative, plus 5 will give us the 4x in the middle. All over the second denominator, 3x times x is 3x squared. Again, 15 is 5 times 3. And we can't put the 3 with the 3 because they would have a GCF then. And if they're both negative, we would have negative 14. Now with the second fraction, we're multiplying by the reciprocal. So now the denominator x squared minus 4 is going to move on top as we factor it. So x squared minus 4 is x plus 2, x minus 2, a difference of squares. And then the denominator is what used to be in the numerator, 3x squared minus x minus 10. We've got 3x times x. And the 10 is 5 times 2. And if we check that, we've got 6 and 5. If the 6 is negative and the 5 is positive, it would give us that negative x in the middle. So now with our fraction, we can divide out the common factors. The x minus 3's are gone. The 3x plus 5's are gone. And the x minus 2's are gone in this problem. Which means left behind in the numerator is just the x plus 2 factor. And in the denominator, the 3x minus 5 factor. And we have our solution. Let's do one more that's just a little bit more involved, but really the same idea extended out to the next level. If we have x to the 2n minus 3x to the n minus 4 over 16x to the 2n minus 9 times 4x to the 2n minus x to the n minus 3 over 2x to the 2n minus 13x to the n plus 20 divided by x to the 2n minus 1 all over 4x to the 2n minus 20x to the n plus 25. Multiplying and dividing in this problem, but really much the same problem. The division means we're going to have to multiply by the reciprocal. We're going to flip that fraction over as we factor it. But first let's factor the first fraction. X to the 2n is x to the n times x to the n. And 4 is 4 times 1 if the 4 is negative and the 1 is positive. Over the denominator is a difference of squares because we've got that even exponent. So it's 4x to the n plus 3, 4x to the n minus 3, times the second fraction, 4x to the 2n. That could be either 4 times 1 or 2 times 2. Let's try 2 times 2 first. 2x to the n times 2x to the n. And 3 is 3 times 1. So that'll give us 2 and 6 as we multiply the outside and inside. And 2 and 6 are not going to give us the 1 in the middle that we want. Switching the 3 and 1 won't make a difference because the 2's are the same on both sides. So instead of 2 times 2, let's try 4 times 4. We're just kind of doing a guess and check here. 4x to the n and 4 times 1, sorry. It's another way to get 4x squared, or 4x to the 2n. So on the outside we have 4. On the inside we have 3. If it's minus 4 plus 3, that would give us the negative 1. We've got our solution. If that didn't work, we could have switched to 3 and 1 and see if that would have helped, but we got it this time. So in the denominator now, 2x to the n times x to the n is 2x to the 2n. Lots of ways to get the 20. One might be 4 and 5. We don't want to put the 4 with the 2, so 4 and 5. Let's see what that gives us. 8 and 5, if they're both negative, would be negative 13. So that's good. For our last fraction, we're going to change it to multiplying by the reciprocal. So the reciprocal in the numerator, we're going to put what was in the denominator. 4x to the 2n, it could be 2x to the n times 2x to the n. 25 could be 5 times 5. And if they're both negative, we get negative 10, and negative 10 is negative 20. So we got that. Over, the numerator is a difference of 2 squareds, x to the n plus 1 and x to the n minus 1. So the only real difference is there's just a lot of factoring in this problem. But now it's much the same. We do our reducing. There's an x to the n plus 1. Whoops. Let me back up. X to the n plus 1. Make sure I grab the right one. There we go. There's a 4x to the n plus 3. There's a 2x to the n minus 5. There's an x to the n minus 4. There's an x to the n minus 1. And so when we do all of our reducing, this one turns out all that's left is 2x to the n minus 5 over 4x to the n minus 3. And we have our solution. So multiplying and dividing fractions, not too bad. Factor it and divide out your common factors, but never, ever, never cancel terms. Always divide out factors. Factors are multiplied, terms are added. What's going to be more interesting to us as we work through these problems, though, are these things called complex fractions. And a complex fraction, also called a compound fraction, is when we have fractions in fractions. And this becomes a little bit of a headache to deal with. The easiest way I have found to deal with these complex fractions is we're going to multiply each term, top and bottom, numerator and denominator, by the least common denominator. Here's what I mean by that. If we have 3 over x squared plus 1 over x all over x minus 9 over x. As I look at my little fractions, there's an x squared, an x, and an x, and don't forget technically this last one is over 1, so it also has a denominator. The common denominator there, if we take the highest exponent, is x squared. And so what I'm going to do is I'm going to multiply each term, top and bottom, by the x squared. because when I do that, x squared will go out with x squared. A single x goes out with a single x, leaving behind one x. In the denominator, again, a single x goes out with a single x, and so what's going to be left is 3 plus x, 1 times x is x, over x squared times x is x cubed, minus 9x. And now we can look at simplifying this. The denominator is a GCF of x. When we factor that out, we have x squared minus 9 under the 3 plus x. But x squared minus 9 is still a difference of squares, so it's x plus 3, x minus 3. And what you notice is the x plus 3's are going to divide out, leaving behind our solution. Notice everything divides out of the numerator. Anything divided by itself is 1, so we still need a 1 in the numerator, over x times x minus 3. And this is considered our simplified complex fraction, multiplying each term by the least common denominator. So let's try another one. Let's do x over x minus y minus 1 all over x plus y minus 1. Here we've got a denominator of x minus y and a denominator of x plus y. We treat those like factors. We are going to multiply everything by x plus y, x minus y. Don't forget to also multiply the 1's by x plus y, x minus y, x plus y, x minus y. And when we do, the x minus y's divide out, and the x plus y's are going to divide out, because I also should have multiplied it by this term. And what is left is an x times x plus y minus x plus y times x minus y all over an x times x minus y minus an x plus y x minus y. Distributing through, we have x squared plus xy minus, this is a sum and a difference, so we've got x times x is x squared, y times y is negative y squared, but be careful, we're subtracting negative y squared, which makes it plus y squared. All over, distributing the x through, we have x squared minus xy. And again, x times x is negative x squared. Y times negative y, subtracting it, makes it plus y squared. So the only simplifying we can do is x squared minus x squared in both top and bottom. And that gives us xy plus y squared over negative xy plus y squared. Well, we can keep simplifying that. Factor out a GCF of y, leaves behind x plus y. Over, factor out a GCF of y, leaves behind negative x plus y. The y's are gone. And so for our final answer, x plus y over, I'm going to move it to y minus x. You could say negative x plus y, but I just think that's prettier. And we have our solution. A little bit of algebra to get there, but nothing too bad. Clear the compound fraction by multiplying by the LCD. Let's try one more example like this. Let's do a over 2 plus a plus 2 minus a over a all over a over 2 plus a minus 2 minus a over a. Again, the 2 plus a, since those are terms, we have to treat those as one big factor, so we've got 2 plus a and a. 2 plus a and a. Our GCF is a times 2 plus a. 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 Multiplying every term, so the 2 plus a's can divide out, the a's can divide out, the 2 plus a's divide out, and the a's divide out. As we do, we want to be careful to keep the numerators of 2 minus a together as a group. We weren't just multiplying the a, we were multiplying the entire thing. So we have a times a, or a squared, plus 2 minus a times 2 plus a, all over a times a is a squared, minus 2 minus a times 2 plus a. Foiling out in the numerator, notice again that's a difference of squares. That's going to save us some work on the FOIL. 2 times 2 is 4, negative a times a is negative a squared. The middle terms are going to subtract out to 0. Over a squared minus 2 times 2 is 4, and again we're going to have minus a negative is a positive, a squared. And this is nice because the a squared subtract out to 0. A squared plus a squared is 2a squared, so we have 4 over 2a squared minus 4. But don't stop there, because there's a GCF we can factor out of the denominator of 2 times a squared minus 2. And then we can reduce 4 over 2 is 2. So for our final answer, we have 2 over a squared minus 2. Compound fractions. Multiply by the common denominator every term. Then multiply it out and simplify. Now another type of compound fraction is one that involves negative exponents. And really these negative exponents aren't any type of new problem. They're exactly like the compound fractions we just saw. The only difference is this one extra step that every term becomes a small fraction. What you need to remember though is we only move the part or the factor with a negative exponent. So let's look at some of these examples. Let's say we've got a to the negative 3b minus ab to the negative 3 all over a to the negative 2 minus b to the negative 2. Negative exponents. Well, each negative exponent is going to make that little piece move to the denominator of a little fraction. But as we do, notice we're only going to move the factor with a negative exponent. So the b stays on top and the a cubed moves down. Minus the a stays on top and now the b cubed moves down. All over, when the a squared moves down, we need a placeholder of 1 on top. Minus when the b squared moves down, we need a placeholder of 1 on top. So the negative exponent simply signifies to us that we need to move down to the denominator of a little fraction. The common error I see people do is they just move things up and down on the single fraction without making these little fractions, this complex fraction. We can only move across a fraction bar if it's all multiplying. Just like we couldn't reduce when there was adding and subtracting, we can't move things around when there's adding and subtracting. So we just make these little fractions instead and solve it as a compound fraction. In the denominators, we've got a cubed and a squared. b cubed and b squared. The common denominator then is a cubed, b cubed. Always taking the highest exponent on each factor. So we'll multiply each term by a cubed, b cubed, a cubed, b cubed. And when we do, the a cubed goes out with the a cubed. The b cubed goes out with the b cubed. A squared leaves 1a behind, b squared leaves 1b behind, and so we have b to the fourth minus a to the fourth all over ab cubed minus a cubed b. Now that we've gotten rid of the compound fraction part of things, that negative exponent, we're going to factor this and see if we can simplify. The numerator is a difference of squares, because those are both even exponents. It's b squared minus plus a squared times b squared minus a squared. The denominator has a GCF of ab. When we factor out ab, we're left with b squared minus a squared, which is kind of nice. We could factor the difference of squares more, but those b squared minus a squareds are just going to divide out right now, leaving behind our final answer of b squared plus a squared over ab. Let's try another one that has negative exponents. Let's do a to the negative 2 plus a to the negative 1 minus 2 all over a to the negative 1 minus 1. Again, because of all that adding and subtracting, we can't just move the a's around. We have to make little fractions. A to the negative 2 becomes 1 over a squared. Plus a to the negative 1 becomes 1 over a minus 2. All over a to the negative 1 becomes 1 over a minus 1. Now with the compound fraction, we look at the denominators to find the least common denominator is a squared. And so we'll start multiplying every term by a squared. Reducing, the a squareds are gone. A leaves behind 1a. A leaves behind 1a. And so now the problem is 1 plus 1a minus 2a squared all over a minus a squared. Now that we've gotten rid of the compound fraction bit of things, we can look at how we can simplify this expression by factoring. 1 is 1 times 1, and 2a squared is 2a times a. To get a positive a in the middle, we want the 2 to be positive on the middle and the negative on the outside. All over, we've got a GCF of a. Factor that out. We're left with a divided by a is 1 minus a. And sure enough, those 1 minus a's will divide out, leaving behind our final answer of 1 plus 2a over a. Completely simplified. Let's do one last problem before we wrap up here. Let's do a plus 1 to the negative 2 minus 1 over a plus 1 to the negative 2 plus 1. Again, with the adding and subtracting between terms, we cannot just move things around. We also cannot do any reducing. We need to first make little fractions. Using 1 as a placeholder, the a plus 1 to the negative 2 moves to the bottom to a plus 1 squared minus 1 all over 1 over a plus 1 squared plus 1. The only denominator we have to work with is the a plus 1 squared. So we'll multiply by a plus 1 squared, a plus 1 squared, a plus 1 squared, and a plus 1 squared. Again, notice we also multiplied the 1's. The a plus 1 squareds divide out quite nicely, leaving behind 1 minus a plus 1 squared, all over 1 plus a plus 1 squared. Be careful of that negative when we distribute it through. It's going to change sign. So we have 1 minus a squared. 1 times a is a, 1 times a is a, so that's 2a. Don't forget to distribute the negative. And 1 squared is 1. Distribute the negative again. All over 1. This time we're distributing a plus. That's going to keep everything positive. A squared plus 2a plus 1. Combine like terms. The 1 minus 1 is 0, so we have negative a squared minus 2a over a squared plus 2a plus 2. And I guess technically in the numerator we can factor out a negative a, leaves behind a plus 2. But that denominator is not going to factor at all, so this time we're not going to get any reducing. So either one of these two answers would be just fine for our final solution. So that's what we're taking a look at on today's assignment, section 1.4, simplifying rational expressions. We can factor and reduce when multiplying. To divide, we multiply by the reciprocal. With complex fractions, we multiply each term by the LCD. And with negative exponents, we make little fractions, turning it into a complex fraction. Take a look at the homework. Let me know if you have any questions. In solving our quadratic equations, often we came up with problems which required the use of complex numbers. Today we're going to take a look at complex numbers in detail. But to kind of set up what they are, I want to look at how mathematicians have worked throughout history real quick. We often have a need for new numbers. I want to emphasize these are not fake numbers. These are actual numbers in order to solve new problems. So the first example that comes along is when the Chinese were trying to solve problems like x plus 5 equals 2. They came up with this revolutionary idea that x is equal to negative 3. They came up with this revolutionary idea that centers around the idea of creating new numbers. They created negative numbers. And this opened up a whole new realm of possibilities of what math can do. Just take, for example, the weather outside in the middle of the winter is a negative number at times. A second example of this was in Egypt. The Egyptians were dealing with problems like x squared equals 7. Whoops. No, they weren't. The Egyptians weren't solving problems like that. They were solving problems like 3x equals 5. Sorry. And they came up with this crazy notion that x equals 5/3. Well, okay, I'm bending history a bit. They used what are called unit fractions, and if you want to know more about unit fractions in the Egyptians, you can Google that. But really, they pioneered this idea of creating these new numbers called fractions. And fractions opened up a whole new realm of possibilities of what mathematics could describe and be used for. So again, another useful breakthrough in the ancient history of mathematics. It was the Greeks that solved problems like x squared equals 7. And they came up with this crazy notion that x could equal technically plus or minus, but we're just going to go with the square root of 7 for now because the Greeks hadn't met the Chinese at that point and worked with negative numbers. they came up with this idea of the square root of 7 being which we cannot write as a fraction. We cannot write as a decimal. So they had to create irrational numbers. Numbers that could not be written as a fraction. Numbers such as pi, the square root of 2, and, in this example, the square root of 7. And there was one other major breakthrough in creating new numbers to make new problems possible to solve, describe, and model with mathematics, and that was the problem that if x squared equals -1. By taking the square root of both sides, we would find out that x is equal to the square root of -1, which isn't a real number. And so we defined it as a new number, I. And in doing so, we created what were called the complex numbers. Now I want to get a hold of the guy who called these imaginary numbers because it creates an illusion that these numbers are fake. The word imaginary numbers was used to be kind of the almost humorous opposite of the real numbers. Well, if they're not real numbers, they must be imaginary. But imaginary does not mean they're fake or some figmentation of some person's imagination. They're actually useful numbers that can be used to describe many things, such as current flow of an electrical circuit. Engineers use these type of problems. I is an actual number. It's just called imaginary. Terrible naming system. Math needs better PR. But, so to avoid this confusion, I'm going to call them complex numbers throughout this video. These complex numbers are actual numbers that are very useful, and we can do a lot of mathematics with them. In fact, most of mathematics looks exactly the same as it did before, with the only definition we need that I squared is equal to -1. Thus, really, I is representing the square root of -1. So now we can solve problems like the square root of -9, because we can split up the square root of -9 into -1 times 9. The square root of 9 is 3, and the square root of -1 is an I. So therefore, the square root of -9 is 3i. Number 2, square root of -5. We can even do things that don't come out pretty because we can split this up to the square root of -1 times 5. And the square root of -1 is I, and the square root of 5 stays inside the radical because we can't take its square root. We can also do negative the square root of -13. Well, we have negative the square root of, we'll take that negative out as a factor of -1 times 13. And then we have negative, the square root of -1 is I, and the square root of 13 is going to stay behind in the radical. Let's take a look at the example, the square root, or how about negative square root of -25. We have the negative out front, square root, -25 becomes -1 times 25. And with a negative out front, the square root of -1 is I, and the square root of 25 is 5, and so we have -5i. We can even make this more interesting and do the square root of, actually let's just make it positive square root. We're going to do the square root of -18, which we can write as the negative square root of -1 times 18, but we can actually even break that 18 down. 18 is 6 times 3 and 3 times 2, so what we really have is the square root of -1 times 2 times 3 squared. And we can take the square root of -1, that's the I. We can't take the square root of 2, so it's going to stay in the radical, but the square root of 3 squared is just 3. And so the square root of -18 becomes 3i square root of 2. Now that's kind of how we can evaluate radicals using I to give us solutions of problems we could not solve before. In terms of manipulating and working with the i's, it's really going to be no different than anything we've seen before. If we are adding or subtracting complex numbers, we will treat the I like a variable. No different than any other variable such as x or y. So for example, if we had 4 plus 3i, a complex number, and we add to it 6 minus 7i, another complex number, a plus in the middle really isn't going to do anything. We can just combine like terms. 4 and 6 is 10. 3i minus 7i is -4i. And we have now added these complex numbers together. How about we try a subtraction problem? We'll take 2 plus 5i, a complex number, and we'll subtract 3 minus 6i. Another complex number. Now this time the minus in between does make a difference because it has to distribute through the entire parentheses. So let's do that. We have 2 plus 5i minus 3 plus 6i. Now when we combine like terms, the real parts, 2 minus 3 is -1. The complex part, 5i plus 6i, is 11i. And we have our solution. Probably two common errors come up with adding and subtracting is one, people forget to distribute that negative sign through the entire problem. That's an important step. The other problem people run into is when they see parentheses, they feel like we have to multiply. Parentheses do not mean multiply. Parentheses just means we have a group. Now, if there's nothing between the parentheses, then we multiply. But in these problems we saw there was a plus and a minus between, so we add and we subtract. Speaking of multiplication, though, how do we multiply complex numbers? Well, almost exactly the same as we multiplied real numbers. We treat the I like a variable. With one little exception, is that the definition of I squared, whenever we have I squared, that's equal to -1. So, going back to our radical examples, if we had the square root of -4 times the square root of -9, if we were to simplify this, the first radical, the square root of -4, the square root of 4 is 2, and the square root of the -1 is I. As we simplify the square root of -9, the square root of 9 is 3, and the square root of the -1 is I. So when we multiply these together, 2 times 3 is 6, and I times I is I squared. However, I squared is -1. Multiplying by -1 is going to change the sign on the problem, making it -6. 6 times negative 1. So that's the only change, is when we multiply by I squared, that's times negative 1. So if we have the square root of negative 6 times the square root of negative 5, we can simplify the square root of negative 6 by pulling the I out, root 6, and we can simplify the negative 5 by pulling the I out, root 5. And so when we multiply together, I times I is I squared. Square root of 6 times square root of 5 is square root of 30. But we also know that I squared is negative 1. So that's the same as saying negative square root of 30. Okay, let's drop the radicals and just start multiplying some complex numbers together. Let's start simple. Let's do 5i times 3i. We've actually already done this. 5 times 3 is 15. I times I is I squared. But I squared is negative 1. So that's 15 times negative 1 is negative 15. How about we do negative 2i times 4 plus 3i? Just like any other algebra problem you've seen before, if we've got something in front of the parentheses, we're going to distribute it through the parentheses. Negative 2 times 4 is negative 8i. Negative 2i times 3i is negative 6i squared. But again, when we see an I squared, that's negative 1. Negative 6 times negative 1 is positive 6. And we still have the minus 8i. I want to be careful here of another trap students run into, is when we start to see I squared equals negative 1, students often will start to make i's equal to negative 1. And i's are not negative 1. It must be squared to become negative 1. If it's just a regular I, leave it as a regular I. How about this one? 2 plus 3i times 5 minus 4i. You'll recognize that when we're multiplying two binomials, this time nothing between the parentheses, we FOIL. So 2 times 5 is 10. 2 times negative 4i is negative 8i. 3i times 5 is positive 15i. 3i times negative 4i is negative 12i squared. And again, we see that I squared is negative 1. So what we really have is 10 minus 8i plus 15i, and then negative 12 times negative 1 is positive 12. And actually, we're not done yet here because we can combine like terms. 10 plus 12 is 22, and negative 8i plus 15i is positive 7i. And we have our product. I want to notice what we've done in all these problems is we put the real part first and then the part with I second. That's going to generally be consistent. We like to put the real part first in our final answer. How about we do 3 plus 2i squared? Well, remember, squaring does not mean we square 3 and 2i and be done. That does not work, because there's a middle term that we have to worry about. So yes, to start off with, we do 3 squared is 9, but then the middle term is 3 times 2i is 6i. 2i times 3 is 6i. And 6 and 6 gives us 12 i's in the middle. Plus 2 times 2 is 4. And I times I, it's bad for it. And I times I is I squared. Again, we see the I squared. I squared is -1. So we have 9 plus 12i plus 4 times -1 is -4. So when we combine like terms, 9 minus 4 is 5 plus 12i. We now have squared this complex number. Here's an interesting one. 2 minus 7i times 2 plus 7i. If we try and FOIL this, I want to notice what happens, and you should be able to see this coming because of problems we've seen before. But 2 times 2 is 4. 2 times 7 is 14i. Negative 7i times 2 is negative 14i. And negative 7i times 7i is negative 49i squared. And why this is interesting is in the middle, 14i, I probably should get the plus in there. 14i minus 14i is 0. That middle stuff should subtract out. And we should have seen that coming by virtue of the conjugates that we were working with. We did this with radicals when we were rationalizing denominators, as we changed the plus and minus in the middle, and now we got rid of the radical in the denominator. Again, I squared is -1, so this is really 4 minus 49 times -1 is now a plus 49, which equals a final answer of 53. But the big one thing I want to notice here is 2 squared is 4, and 7 squared is 49. Normally with the difference of squares we had a minus in the middle, but with complex numbers there's a plus in the middle. We're adding the squares of the numbers, which leads to a nice general case. If we multiply a plus bi times a minus bi, a and b are the numbers we're working with. I is the square root of -1. When we multiply it out, first off, we know from our past experience that the middle stuff is going to subtract out to 0. So all we really need is a times a is a squared, and bi times negative bi is negative b squared, I squared. But as has been the case this whole time, is I squared is -1. So we have a squared minus b squared times -1 is a positive b squared. So what we notice is if we are multiplying complex conjugates, we have a plus bi, a minus bi. One's positive, one's negative, and they're complex. They've got an I in there. We can just square both parts and add. And when I say parts, I mean the numbers, the a and the b. Or in example 7, it would have been the 2 and the 7. In example 2, we could have noticed this pattern sooner and said, well, 2 squared is 4, plus 7 squared is 49, and gotten straight to the answer. It only works with conjugates, but it's very important when we start talking about how we divide complex numbers. The whole idea behind dividing complex numbers and what we're going to do here is that we can have no square roots in the denominator. And remember, I is a square root. We don't like to have square roots. We don't like to have i's in the denominators. And so the way we fix it is the same way we fixed it with regular radicals. Notice again, I is no different than anything else. We multiply by the conjugate. And the nice part when multiplying by the conjugate, at least in the denominator, is we just have to square both numbers and add. So for example, if we have 2 minus 3i over 5 plus 4i, we don't like that I in the denominator, so we're going to multiply by its conjugate by changing the sign to 5 minus 4i in both numerator and denominator. Now we're going to have to work for the numerator. The numerator we actually have to FOIL out. No shortcuts. It's not a conjugate, so we have to go through all the FOILing. 2 times 5 is 10. 2 times negative 4i is negative 8i. Negative 3i times 5 is negative 15i. Negative 3i times negative 4i is positive 12i squared. All over. In the denominator, we're going to take our shortcut. We don't have to worry about the i's because we know we have to square both numbers and add. So 5 squared is 25. We know it's going to be a plus because they're complex conjugates. 4 squared is 16. Now again, I squared is negative 1. So I'm just going to fix right now. That negative 1 is going to change that plus into a minus. So now we can combine like terms. 10 minus 12 is negative 2. Negative 8i minus 15i is negative 23i. All over 25 plus 16 is 41. We can't factor and reduce, so this is our final solution. Let's try one last problem with division. 7 minus I over 3 minus 2i. Again, we don't like the I in the denominator, so we're going to multiply by its conjugate of 3 plus 2i. We'll do the same thing in the numerator, multiplying by 3 plus 2i. We simply change the sign in the middle of the denominator. And again, we will FOIL out the numerator. 7 times 3 is 21. 7 times 2i is positive 14i. Negative I times 3 is negative 3i. And negative I times 2i is negative 2i squared. All over the denominator's complex conjugates, so we can use our shortcut. 3 squared is 9, plus 2 squared is 4. Again, I squared is negative 1, so I'm going to cross that off and change the minus 2 to a plus 2. Because negative 2 times negative 1 is positive 2. And then we just have to combine like terms. 21 plus 2 is 23. 14i minus 3i is plus 11i. All over 9 plus 4 is 13. And we have our final solution. This is complex numbers. Not a unreal number, but it is the opposite of the real numbers. It boils down to we treat I as a regular variable, with the only exception that I squared is -1 to help us simplify expressions. Take a look at the homework where you will add, subtract, multiply, and divide complex numbers. Section 1.6 gets at the important concept of completing the square. This is a process that we did use in our pre-college math experiences when we were solving equations by completing the square. Now, solving these equations, we had the advantage of working on both sides of the equation, so some problems became easier as a result. For instance, we had something like 3x squared plus 18x plus 12 equals 0. And the first thing we did in these problems was we subtracted c, or that third term, from both sides. And so when we subtracted that 12, that left us with 3x squared plus 18x equals -12. The next thing we did was we divided each term by e. By a. Where'd the e come from? A is the first term in front, so when we divide everything by 3, the 3 divides out and we're left with x squared plus 6x equals -4. And now we get to what is actually called the completing the square step. The process of completing the square is finding this value that we are going to add to the equation. We're going to add 1/2 of b, the middle term, squared to both sides. So b here is 6, so half of 6 squared. Well, half of 6 is 3, and 3 squared is 9, so we're going to add 9 to both sides. And when we do, we get x squared plus 6x plus 9 equals 5. And then finally, the next step we would take would be to factor and solve. And the nice part is we know it's going to factor to something squared. That's why we added the 1/2 of b to both sides. So we take the square root of the first term. The square root of x squared is x. We always take the sign from the middle, which is plus. And we take the square root of the second term, 9, which is 3, and make that equal to 5. And then we continue by solving from there. The opposite of squared is to take the square root of both sides. Squared and square root are opposites. So we have x plus 3 equals plus or minus 5. Subtract 3 from both sides, and we have our final answer that x is -3 plus or minus the square root of 5. The big thing here, though, that is really what's called completing the square is step 3, when we take that 1/2 b squared, 1/2 of b squared, I should say, because we do the half first, and use that to make something that's a perfect square. We're going to go through a very similar process for today's lesson to do what is I'm going to call completing the square on an expression. And the difference between an expression and an equation is with an expression there is no equals, which means we can only work one side of the equation. which means we're going to have to tweak this process a little bit. Same problem again, 3x squared plus 18x plus 12, but this time it's not equal to anything. It's just an expression that stands alone. So there's no solving. We'll never know what x equals. Instead, we're going to make this into a prettier, more useful form. In our future units, we're going to look at graphing equations. And when we graph the equations, some forms are more useful than other forms to help us make a quick and easy graph. Completing the square puts it into a useful form. So right now we're going to look at the complete the square process, and then in a future chapter we'll look at how that useful form can turn into a graph. But for now, the first step we're going to take is going to be to factor a out of the first two terms. This is similar in the solving when we divided both sides by the a. Here we can't divide both sides by a because we only have one side to work on. So instead, we're going to focus on the first two terms, and we're going to factor the a out. We'll factor the 3 out, leaving x squared plus 6x. Plus 12, notice, is outside of the parentheses. The next step we're going to do is our actual complete the square step. We're going to find that 1/2 of b squared. We're going to do two things with it. We're going to add it inside the parentheses, but we can't do the same thing to both sides. So we can't add it to the left and add it to the right. So to stay balanced with something that we've added, we have to subtract it. Leave a space. Subtract it from the end. Now in the space here, I'm going to make a note that we need to also multiply by a. Because when we add it inside the parentheses, you could think about that 3 could potentially distribute through the parentheses, which means it's also going to distribute to the number we add inside. So to stay balanced, to make sure we didn't add any more than we took out, we are going to need to subtract a times that magic number that completes the square. So in this case, again, half of 6 is 9. I'm sorry, half of 6 is 3. And 3 squared is 9. So we're going to add 9 inside the parentheses. And we're going to subtract 9 times the a outside the parentheses. When we do that, we have 3 times x squared plus 6x plus 9 plus whatever 12 minus 9 times 3 is. So step 3 to finish this off is going to be, instead of factor and solve, we're going to factor and simplify. 3 stays out front. The parentheses are always going to be a perfect square because we picked the number 9, which would force it to be a square. So we take the square root of the first term, which is x, the sign from the middle, plus, and the square root of the 9, which is 3. Then we simplify the last part. 9 times 3 is 27, and 12 minus 27 is negative 15. We have now completed the square on the expression. These 3 steps that we have outlined in blue, green, and orangish yellow, whatever you call that, probably more orange, are going to be the 3 steps that you're going to use on every problem on the 1.6 homework. This process is one you need to know very well, especially when the problems become a little bit more involved, like involving fractions. Now we go through the same process, the same 3 steps. We just might need to use fractions along the way. For example, if we have 8x squared minus 24x plus 13. Step 1 was to factor a out of the first 2 terms. So we factor 8 out, leaves behind x squared minus 3x plus 13. Step 2 is to complete the square, which means we're going to find half of b is 3, squared. Well, that's 3 halves squared, and we remember to square a fraction, we square the numerator and denominator. So that's 9/4. Fractions are okay. We're going to add 9/4 inside the parentheses and subtract 9/4 outside the parentheses times a, which is 8. So now when we factor and simplify, we know it's going to factor to a perfect square. Square root of the first term, the square root of x squared is x, sign from the middle, and then we'll take the square root of the last term, the square root of the 9/4. Just like our exponent property to square top and bottom, with square root, we will take the square root of the top and bottom. Square root of 9 is 3, square root of 4 is 2. And then we have to simplify the 13 minus 9/4 times 8. What's nice here is 8 over 4 is 2, and 9 times 2 is 18. So that's 13 minus 18, which is going to be a -5. And we have now completed the square, putting the expression into what's going to be a more useful form to help us with things such as graphing or analyzing the expression. Let's try another example with some fractions. This one didn't use a lot of fractions. Maybe this one will be more interesting. How about we try 3x squared plus 15x plus 10. Now let's do plus 12. Change the problem a bit, make it a little more interesting. Same 3 steps we're going to go through again. First, we're going to focus on the first 2 terms, and we're going to factor a out of the first 3 terms. So when we factor a 3 out, we're left with x squared plus 5x plus 12. Again, now we will complete the square by finding 1/2 times b, which is 5, squared. That becomes 5 halves squared, or 25 over 4. So we're going to add 25 over 4 and subtract 25 over 4 multiplied by the 3 out front. Now when we factor and simplify, we have 3 times the square root of x squared is x. Take the sign from the middle, plus, and the square root of the fraction, 25/4, top and bottom. The square root of 25 is 5. The square root of 4 is 2, squared. Now we're going to have to do a little bit more work to evaluate this mess over here on the side. First, in order to subtract, we're going to need a common denominator. Right now that 12 is over 1, so we're going to have to multiply by 4 over 4. So that's going to give us 48/4 minus 25 times 3 is 75/4. 48 minus 75 then is going to give us -27/4. And that'll become our final solution. Let's try one more, even more interesting fraction problem. Let's look at 5x squared plus 3x minus 2. It doesn't feel like there's fractions. There are. Grouping the first two terms together, we factor out a. Here a is 5. But 5 doesn't factor out really nicely out of the 3x. That's okay, we just need to have an answer that is a fraction. So when we have 3 and we divide out 5, what's going to be left is 3/5 x minus 2. So we end up with a fraction in the middle. Now when we complete the square, we take 1/2 times b, which is 3/5 squared, or 3/10 squared. 3 squared is 9, 10 squared is 100. We are adding 9 over 100 inside the parentheses and subtracting 9 over 100 times 5 outside the parentheses. Now we have 5 times square root of x squared is x, sign from the middle is plus, and the square root of the fraction, 9 is 3, over 100 is 10, squared. Then we have to deal with this mess again. Fortunately, the 5 over 100 is going to reduce, leaving 20 behind in the denominator. So 20 is our common denominator. So we're going to multiply times 2 times 20. And that's going to give us negative 40 over 20 minus 9 over 20 is negative 49 over 20. And we have our final solution. This process of completing the square on an expression goes through the same 3 steps every time. You should have these 3 steps memorized. First, we factor out the a, even if it makes a fraction. Second, we complete the square by finding 1/2 of b and squaring it. Add it inside the parentheses, subtract it times the a at the end, and then factor and simplify. Where this process is going to be useful is when we're working with some complex expression that has a quadratic portion. For example, we might have 1 over 2x squared minus 16x plus 5. And you notice it's got a portion down here that's a quadratic. When we get to graphing in our future chapters, this is going to be very difficult to graph the way it looks. But if we were to complete the square on that quadratic portion, it becomes very easy to graph. So let's look at how we can complete the square on that quadratic portion. So just looking at the 2x squared minus 16x plus 5, the quadratic portion, we first factor a out of the first 2 terms. Factoring out of 2 leaves x squared minus 8x plus 5. We then complete the square by taking the middle term negative 8 and dividing by 2 and squaring it. Half of negative 8 is negative 4. Squared is 16. So we're going to add 16 inside the square root and subtract 16 times the front number, 2, from the end. When we factor, this is going to give us 2 times stuff squared. The square root of x squared is x. Sign from the middle. Square root of 16 is 4. And then when we do the 16 times 2, that's 32. 5 minus 32 is negative 27. And so now the expression becomes 1 over, going back to the original expression. Now it's 2 times x minus 4 squared minus 27. We have completed the square on the quadratic portion of the problem. Let's try another one. How about we do the fifth root of negative 4x squared plus 5x minus 2. Again, we'll notice that this has a quadratic portion in it. So we're going to focus on the quadratic portion, the negative 4x squared plus 5x minus 2. Going through the exact same steps, group the first two terms together and factor out the a, in this case the negative 4. When we factor out a negative 4, it now becomes positive x squared and negative 5/4 x minus 2. Be careful with the negative in your signs here. Now we're ready to complete the square by finding 1/2 of b squared. 1/2 of negative 5/4 squared is negative 5/8 squared, which is a positive 25 over 64. So we're going to add 25 over 64. And from the end, subtract 25 over 64 times the front term, which notice is a negative 4. Now when we factor and simplify, we have negative 4 times stuff squared. The square root of x squared is x. Sign from the middle. And the square root of 25 over 64 is 5/8. And then we have this mess to deal with. One thing I notice is a negative times a negative is a positive. So now we're actually adding at the end. And 4 over 64 reduces to a 16 in the denominator. 2 is currently over 1, so the common denominator is 16. We will multiply by 16, top and bottom. And that gives us negative 32 over 16. And now it's plus 25 over 16. Negative 32 plus 25 is 7. And it's going to be negative, so negative 7/16. And we have now completed the square on the quadratic portion. Sticking that back into the original expression, which was a fifth root of negative 4 times x minus 5/8 squared minus 7 over 16, we have completed the square on the quadratic portion of the problem. So by way of review, we've got 3 steps that we're working through to complete the square on an expression. Every problem exactly the same. We'll factor a out of the first 2 terms. Then we complete the square by finding 1/2 of b and squaring it, adding inside the parentheses, subtracting times a from the end to stay balanced, and finally we factor and simplify. Section 1.6 is short, only a few problems in it. Take a look at them, complete the square, and we will see you in class. Section 1.7 takes a look at how we solve basic formulas in a little bit more of an abstract way. We're going to have more variables than just x, but we're just going to be solving for one of the variables. And so to start off with, we'll look at some basic formulas, and some of these you may have seen before. If I can spell formula right. There we go. For example, we might have solved an equation like area equals length times width times height for maybe the width. What this means is we're going to solve for the variable w. We want to get that variable w alone, and we will treat the other variables as constants. And a constant is just a fancy way of saying numbers. So just like we would solve 5 times w by dividing by 5, L times w will clear the L by dividing by it. Similarly, we can clear the times h by dividing by the h. So we divide both sides by LH, and the L's and H's divide out, and the w is alone, which is exactly what we want. The width is equal to the area divided by the product of the length times the height. We have now solved for, gotten the w alone. That's our goal with solving these formulas. So if we have, for example, the formula for the area of a diamond, the area is equal to 1/2 times diagonal 1 plus diagonal 2, we could solve this for one of the diagonals. How about diagonal 1? That means I'm going to treat diagonal 1 like my variable, and the other stuff is all just numbers. We can clear the fraction in one of two ways. We can distribute the fraction and deal with it along the way, or we can clear the fraction right at the beginning, and I'm going to do that by multiplying both sides by 2. Clears the denominator of 2. So we have 2a is equal to d1 plus d2. Remembering our goal, is not to erase d1, it is to highlight d1. Our goal is to solve for the d1, getting that d1 alone, and we can do that real quick by subtracting the d2 off. Just like if that were a number, we would subtract that number off the end. Now notice we do not have like terms, so there's no combining on the left. We just have 2a minus d2 is equal to d1. And now that that d1 is alone, we have our final solution. Now along the way as we're solving these formulas, on occasion it turns out that the formula is asking us to solve for a variable that is in 2 different locations, or 3 or 4, more than one location. So we can't just get it alone. Instead, we might have to think that factoring may be required. And usually this is just factoring of a greatest common factor, or specifically not the greatest but the variable we want. Which means in order to do this we're going to have to separate the variable, that's the one we're solving for, from the constants, or the parts that we are not solving for. So let's take a look at an example where we do just that. How about this example? We have ax plus by equals cx minus dy. We're going to solve it for both x and y. So really this is 2 different problems. We're going to solve it for x, and then we'll come back and look at it again and solve it for y. So first, when we're solving for x, you notice we've got the x's in 2 different places. We need to get those x's all on the same side of the equation. So I'm going to subtract cx from both sides. And that's going to move all of the x's to the left side. Anything that does not have an x, though, we want out of the way. Notice we have that plus by on the left side. There's no x's there. We want it out of the way, so we will subtract by from both sides. When we do, the left side, ax minus cx, every term has the variable we're looking for. On the right side, negative dy minus by, has no x's. Since every term now has that x that I'm looking for, we can factor that x out, leaving a minus c equals negative dy minus by. And the reason this is nice is that now puts all the x's in one place. X times the stuff. We can then get rid of the stuff by dividing it out as a group, a minus c, which leaves us just with x equals negative dy minus by over a minus c. That's solving the equation for x. However, we were also asked to solve it for y, so now we'll do it again. I'm just going to copy the problem down again for us. ax plus by equals cx minus dy. But this time we're solving it for the variable y. And again, we see that the y is in two different places. We need to get those y's all on the same side. And it doesn't matter which side. I'm just going to move them to the left side by adding dy to both sides. Now all the y's are on the left. We want everything else on the right. So we do that by subtracting ax from both sides. Now we have by plus dy equals cx minus ax. And again, with both y's on the same side, we can now factor those y's out, leaving us with just b plus d equals cx minus ax. Now we have y times the stuff. We can divide by the stuff, b plus d. And that leaves us with our final answer that y is equal to cx minus ax over b plus d. Our final solution. Now these equations can become quite complicated and involved, but the process and the idea behind them is exactly the same. If we were doing 3 times a plus b minus ab equals 5 times a plus b, we can solve this equation for a. And notice we have several a's. We're going to have to get all those a's on one side and everything without an a on the other side. Of course, these parentheses get in the way. So how do we handle the parentheses? Well, we know we can distribute through parentheses. So we have 3a plus 3b minus ab equals 5a plus 5b. Now we're going to look at where our a's are. We've got an a in the first term, in the second term, and just after the equal sign. We want all the a's on the same side, so it's probably easiest to move them to the left. We'll subtract 5a from both sides. Line up the like terms. And we need to get rid of that 3b because there's no a's on it, so we'll subtract 3b from both sides. Lining up the like terms. So now we've got 3a minus 5a. Notice those are like terms. The variable part does match. So we have negative 2a. Still have the minus ab equals 5b minus 3b is 2b. Now we can factor out the a that is in common in both, leaving behind negative 2 minus b equals 2b. Finally, get the a alone by subtracting both sides by that group. Dividing both sides by that group. Negative 2 minus b. And we're left with a is equal to 2b over negative 2 minus b. Let's try one more of these. How about we do x plus y times 3 minus x equals 5xy. And we're going to solve this equation for y. Again, we need to get rid of the parentheses here in order to get at the y's that are on both sides of the equation. We get rid of the parentheses by FOILing it out. So we have 3x minus x squared plus 3y minus xy equals 5xy. Now we want to get all the y's on one side. I notice we've got 2 of them on the left and 1 on the right. So let's move them over by subtracting 5xy from both sides. Lining up the like term, lining up the xy. And then we'll get rid of the things that don't have an xy. So we'll add x squared, that don't have a y, and we'll subtract 3x. So we'll add x squared and subtract 3x from both sides. That leaves us with 3y minus xy minus 5xy is minus 6xy equals x squared minus 3x. Now we can factor out that y from each term, leaving behind 3 minus 6x equal to x squared minus 3x. Finally get the y alone by dividing by the 3 minus 6x. And we're left with y equals x squared minus 3x over 3 minus 6x. We can't reduce because of the adding and subtracting. Remember, we can only reduce if it's factored. And we could try and factor it to see if it reduces. This one doesn't, because when we do factor, we get x times x minus 3 over 3 times 1 minus 2x. So it does not reduce. Either answer would be acceptable. So that's kind of how we can handle it when factoring is going to be required. One other bump in the road that might come up, though, is fractions that seem to make everything more difficult when they don't have to. Because really, whenever there's a fraction, we will clear the denominator by multiplying both sides by the least common denominator. So for example, if we have 3 over a plus 2 over b equals 5 over ab, and we want to solve for b. First thing we'll notice is the denominators each have factors of a and b in them. So the least common denominator is going to be a times b. So we're going to multiply each and every term on both sides by that least common denominator. The advantage there is the a's divide out of the first term, the b's divide out of the second term, and both a and b will divide out of the third term, leaving us with 3b plus 2a equals 5. Now, with no fractions, this problem is just as easy as the first problems we started with. Solving for b, we know to take care of adding and subtracting first, so we will subtract 2a from both sides, leaving behind 3b equals 5 minus 2a. Getting the b alone, we'll divide both sides by 3, and our final answer is b equals 5 minus 2a over 3. So not too bad. Clear the fractions by multiplying by the LCD. One thing to watch out for, though, as we do that is if we have something like v equals q over e times 1 over r1 plus 1 over r2, and we want to solve it for r1. Yeah, let's do r2. We did d1 last time. We'll do r2 this time. Here we have a product of a fraction and parentheses. We cannot do the LCD of the overall thing. We have to do it almost in two pieces. We either can first distribute and then clear the fractions, Or we can clear the fraction outside the parentheses and then clear the fraction inside the parentheses. I like the distributing idea, so I'm going to distribute through the parentheses. That's going to give me v equals q over e r1 plus q over e r2, multiplying fractions straight across. Now for our least common denominator, we see factors of e, r1, and r2. So that's what we will multiply both sides by, e, r1, r2, e, r1, r2, e, r1, r2. And that's nice because the e and the r1 will divide out of the first fraction, and the e and the r2 will divide out of the second fraction. And so we're left with v, e, r1, r2 equals q, r1, I'm sorry, q, r2, the r2 is left here, plus q, r1. Now we've got something we might have seen in Part B, where we've got our variable that we're solving for. Remember, we're solving for r2 in two different places. Let's get all those r2's on the same side by subtracting qr2 from both sides. When we do, we get VE R1 R2 minus QR2 equals QR1. Solving for R2, we can factor that R2 out, so we only have a single one we are solving for. VER1 minus Q equals QR1. And finally, to get the R2 alone, we divide by the VER1 minus Q on both sides. And when we do that, we have R2, the only R2, all alone, is equal to QR1 over VER1 minus Q. It looks ugly, but what's important is the R2 is alone, it's the only one, equal to that formula. We are done. Now, these ideas of solving formulas for variables can be extended on to some other really interesting, I think we're on D, other really interesting problems. And we can use much the same principles in order to solve them. Let's say we have a is equal to the square root. Let's even make it plus or minus the square root of ab over c times the square root of d squared minus d. And we're going to solve for capital D. Well, one way to get at this is we can clear the square root so we can actually work the problem by squaring everything. And since these are factors, this would not work if there was adding or subtracting in the middle. But since they're multiplied together, we can square both parts. So we have a equals 2, plus or minus squared is a positive. Square root squared gets rid of it, so we're left with ab over c. Times square root squared is d squared minus d. We're getting close. Now we just have to clear that fraction by multiplying by c. So we have ac equals ab times d squared minus d. Notice the difference between capital and lowercase. That's important. And then let's see, we can go two directions. Both of them are equally valid at this point. We can either distribute the AB or we can divide by it. I'm going to distribute it. So we have AC equals d squared AB minus ABD, all lowercase. We're solving for the capital D, so I'm going to add the AB lowercase d to both sides, get it out of the way, so that we have the variable on one side and everything else on the other side. AC plus ABD equals d squared AB. Divide both sides by AB, leaving just the d squared alone. we have AC plus ABD, all divided by AB equals D squared. And what's nice about this, we can simplify a bit. Notice the numerator, we can factor out a GCF of A equals C plus BD over AB equals D squared, and that's nice because the A's divide out. We can only do that if we factor first because of that plus in the middle. So now we have D squared equals C plus BD over B. And finally, to get rid of the squared, we take the square root of both sides. Remember, when we take the square root of both sides, we have plus or minus the square root of C plus BD over B. But don't get too excited. We're not done yet because that left side has a problem with it. Remember, with square roots, we can take the square root of the top and bottom, the square root of C plus BD over the square root of B equals D. But we don't like to see square roots in the denominator. So to clear the square root, we'll multiply by the square root of B in numerator and denominator. Oops, I think I changed my capital to a lowercase. I just warned you not to do that. When we rationalize the denominator, then we have plus or minus the square root of, all that's under a square root, so we can just leave it as a factor, B times C plus BD, all over square root of B times square root of B is just B, and that is what D is equal to. So a bit of an involved process, but the pattern and the idea is still the same. We want to get at that variable that we're solving for. If needed, we get all that variable on one side, everything else on the other side, and then we can isolate that variable. Let's actually summarize this in a simple process review. So we have a clear guideline of how to solve these linear formulas. First thing we might want to do is clear any parentheses. And we can do this simply by distributing. Once we clear the parentheses, if there are any, we can clear any fractions. And we do that by multiplying by the least common denominator. And that's going to give us a nice linear formula that we can separate the variables from the constants. And remember, constants and variables are in quotes because usually there's lots of variables that we're working with. But the only thing we're actually going to call a variable is the variable we're looking for. Everything else we treat like a constant. Once those are separated, if you've got several variables on one side, you might have to factor the variable so that we can isolate it by dividing both sides to solve your formula. So that's the process we're going through today. There's lots of different varieties of these formulas that you'll take a look at on the homework assignments, so take a good look at them. Come to class with questions. We will see you in class. Section 1.8 gets at the concept of absolute values in equation form and in inequality form. This should be a review of your pre-college math experiences, but just as a review, we're going to look at each of these types of problems. First with equations. And with equations, we're going to look at the example that the absolute value of some number is equal to 3. And think about what possible values could go into an absolute value to give us a solution of 3. Well, we know that the absolute value of 3 is 3, and the absolute value of negative 3 is 3. In other words, we've got two possible situations for what can go inside the absolute value, both the positive and the negative. So we're going to need to solve an equation for both the positive and the negative. Before we do that split up, though, there's an important first step we need to remember, is we first must isolate the absolute value. Then we will consider the plus or minus, the positive or the negative. So for example, if we've got the absolute value of 3x minus 4 equals 7, the absolute value here is completely alone, so all we need to do is consider what values inside the absolute value could give us a 7, which would be either positive 7 or negative 7. So 3x minus 4 might equal positive 7, or 3x minus 4 could equal a negative 7. And then the absolute value would make it positive. In other words, the way we remove an absolute value is by considering both the positive and negative solutions. So to solve then, we add 4 to both sides in the first equation. 3x equals 11. And then divide both sides by 3 to find out x is 11/3. The second equation solves exactly the same in this case. We're going to add 4 to both sides. Gives us 3x equals negative 3. Divide both sides by 3, and x could equal negative 1. So our two solutions here are 11/3 and negative 1. Let's look at a bit more of an involved problem, though. Let's do negative 2 times the absolute value of 5x plus 3 plus 6 equals negative 4. Now this problem's a little different, and the common error we see students do is they will rewrite this with a positive 4 and a negative 4. And that is incorrect, because that process gets rid of the absolute value, but the absolute value here is not alone. We've got negative 2 times the stuff plus 6. We have to get rid of that negative 2 times the stuff plus 6. And so just like solving other equations, we'll first get rid of the adding and subtracting by subtracting 6 from both sides, leaving negative 2, absolute value of 5x plus 3 equals negative 10. And then finally get the absolute value alone by dividing by negative 2. And when we do, we have the absolute value of 5x plus 3 equals positive 5. Now that the absolute value is alone, now we can consider the two equations, stripping off the absolute value. 5x plus 3 equals 5, and 5x plus 3 equals negative 5. And solve these equations. Subtracting 3 from both sides gives us 5x equals 2, and dividing by 5 gives us x equals 2/5. The other equation, solving the exact same way, subtracting 3 gives us 5x equals negative 8, and dividing by 5 gives us x equals negative 8/5. And we have our two final solutions. So in summary, absolute value equations get the absolute value alone, and then strip the absolute value by considering the positive and negative solutions. That's really all there is to equations. A few more things to look at, though, when we're talking about inequalities. Let's kind of set this up by saying the absolute value of a number is less than 2. And I want to recall what this really means. A lot of the times we get distracted with absolute value by saying, make it positive. But that's not really what absolute value means. Absolute value means the distance from 0. So what we're really saying with this inequality is that the distance from 0 is less than 2. In other words, if I have a number line here with 0 in the middle, 2 and negative 2 out to the sides, we want to know where is the distance from 0 less than 2. Notice this entire blue line, anywhere along that blue line has a distance of less than 2. So we're going to be actually between negative 2 and 2. In interval notation, negative 2 through positive 2. This is what we're going to use in order to solve our absolute value equations. When we see that the distance is less than 2, we will say A is between the positive 2 and the negative 2. Notice the negative goes on the left. That's important. The small number first. So if we were to work an example, say the absolute value of 3x plus 5 is less than 4, we know that means the 3x plus 5, because it's less than, has to be between negative 4 and positive 4. Then we solve from here. When we subtract 5, we have to subtract 5 from all three parts, giving us negative 9 is less than 3x, which is less than negative 1, and then divide each part by 3. And x is between negative 3 and negative 1/3. In interval notation, we go from negative 3 to negative 1/3. Anything in that range will make this inequality a true inequality. Let's try another example. How about we do the absolute value of 5x plus 1 over 2 is less than or equal to 3. Again, because the absolute value is less than, we'll say 5x plus 1 over 2 is between, with the or equal to, negative 3 and positive 3. We can start solving by getting rid of the fraction by multiplying everything by 2. That'll divide out in the middle, leaving us negative 6 is less than or equal to 5x plus 1, which is less than or equal to positive 6. Subtracting 1 from all three parts gives us negative 7 is less than or equal to 5x, which is less than or equal to 5. And finally, dividing by 5 to get the x alone gives us negative 7/5 less than or equal to x, less than or equal to 1. Or in interval notations, with square brackets, because we're or equal to, we're between negative 7/5 and 1. Let's try one more example that might be a little bit more involved. How about we do 4 minus 2, absolute value of x plus 1, is greater than negative 2. Again, just like with solving with equations, we don't like to see the absolute value hanging out with a bunch of other stuff. We need to get that absolute value alone before we decide what to do with the inequality. We can get it alone by subtracting 4 from both sides, giving us negative 2 absolute value of x plus 1 is greater than negative 6. Then we can divide both sides by negative 2 to get rid of that 2 in front, giving us the absolute value of x plus 1 is less than, remember when we divide by a negative, the inequality flips over, 3. I want to notice a couple things we did as we got that absolute value alone. First thing, we did not do 4 minus 2 to get 2. We can't combine them because they are not like terms. The 2 has an absolute value on it. The 4 does not. Not like terms. Another thing I want to notice that we did is we did not distribute the negative 2 through the parentheses. We will never, ever distribute through absolute value, because distributing could potentially change the sign and as a result change the solution. Always divide out a coefficient in front of the absolute value. And thirdly, very important, when we divided by a negative, the inequality flipped over. Don't forget, when we divide by a negative, to switch the inequality. Now we have the absolute value is less than a number. We know when the absolute value is less than a number, it means it's squeezed between the negative 3 and the positive 3. And we can solve this equation quite nicely by subtracting 1 from all three parts, giving us negative 4 is less than x is less than 2, or an interval notation with a curved bracket, because it's just less than, we're between negative 4 and 2. So when the absolute value is less than a number, we set up this tripartite inequality because the distance is less than 2. It's between two numbers. That's different than if the absolute value were greater than 2. Because now we're saying the distance from 0 is more than 2. And so if we were to think about that on a number line, we want distances that are greater than 2 away from 0. That'd be from 2 up. Those all have greater distances. Or from negative 2 down. Those distances from 0 are again greater. So we're going the other direction. And we jump over a gap with a union. So we will say from negative infinity, which is all the way to the left, to negative 2, union, jumping the gap from 2 to positive infinity. Or to set up an equation that we would otherwise solve, we would say that the a is greater than 2, like it's written, or means union, that's jumping the gap. A is, to get the other side, we switch the inequality and switch the sign. Greater than 2 or less than negative 2. In fact, usually I'll switch these around just to help out. A is less than negative 2 or A is greater than 2. Because we like the negative to come first, we like to go smallest to largest. And that's also going to correlate the negative 2 with the negative 2 and the positive 2 coming second. So that just kind of goes together better. Although technically the order of the inequality doesn't matter. So now we see the absolute value of 5x minus 3 is greater than or equal to 1. Notice this is different than the problems we solved in B1 in our notes up above, because now the inequality is greater than a number. When it's greater than a number, we will say the 5x minus 3, switch the inequality, switch the sign, is less than negative 1. Or the 5x minus 3, just like it's written, is greater or equal to 1. And we'll solve both of these. By adding 3, we get 5x is less than or equal to 2. Dividing by 5, x is less than or equal to 2/5. Or, solving the other equation by adding 3, we get 5x is greater than or equal to 4. Dividing by 5, we get x is greater than or equal to 4/5. which means in interval notation, because negative infinity is on the left, we have negative infinity up to 2/5. Or is a union, and then x is greater than 4/5. So we're going to go from 4/5 to infinity for our final solution. So a little different when the absolute value is greater than a number. We do a union. Flip the inequality, flip the sign. Let's try another example. How about we do the absolute value of 3x minus 5 over 2 is greater than 5. And actually, making me think, up here, our previous answer, we have a mistake. Because we've got that or equal to line, we should at 2/5 have a square bracket, and we should at 4/5 have a square bracket. Square brackets when it's or equal to. Compared with example B here, we're not going to have a square bracket because it's just strictly greater than. Again, though, we'll notice because it's greater than, we'll say the 3x minus 5 over 2, switch the sign, switch the symbol, less than negative 5. Or the 3x minus 5 over 2 is, just like it's written, greater than 5. Clear the fraction by multiplying by 2. Gives us 3x minus 5 is less than negative 10. Add 5. 3x is less than negative 5. Divide by 3 to get x is less than negative 5/3. Or, going through almost the identical process on the other side, multiplying both sides by 2. 3x minus 5 is greater than 10. Adding 5 to both sides, 3x is greater than 15. Dividing by 3, x is greater than 5. And so in interval notation, let's do it in pink, negative infinity, bad infinity, negative infinity to negative 5/3, or is the union, and then 5 up to infinity. Let's try one really involved problem. How about we have 5/3 minus 1/6 times the absolute value of x plus 1 over 5 is less than 1/3. Now you might notice that this guy has an absolute value in it and a less than. So does that mean we're between two numbers? Well, we can't make that decision until the absolute value part is alone. So we have to get it alone by dealing with all the fractions outside of it. Well, let's make those fractions easier to work with. Let's clear the fractions by multiplying by the LCD of 6. 6 over 3 will reduce to 2, so 2 times 5 is 10, minus 6 over 6 is 1, absolute value of x plus 1 over 5, is less than 6 over 3 reduces to 2, 2 times 1 is 2. Still working on getting the absolute value alone, we have to subtract the 10 from both sides, because we cannot subtract the 1 and combine because those are not like terms. So we have negative 1, absolute value of x plus 1 over 5 is less than negative 8. Divide both sides by the negative 1 because we can't distribute it. And when we divide by a negative, the inequality is going to flip over. So we have the absolute value of x plus 1 over 5 is now greater than positive 8. Which means now we treat this absolute value like it's a greater than absolute value. Greater means we're going to set up the or. X plus 1 over 5 is, switch the sign, switch the symbol, less than negative 8. Or x plus 1 over 5 is, keep it the same, greater than 8. And solve these remaining equations. Multiplying by 5 gives us x plus 1 is less than negative 40. Subtract 1, and x is less than negative 41. Or, same thing on the other equation, we'll multiply by 5 to clear the fraction. X plus 1 is greater than 40. Subtract 1, and x is greater than 39. And then writing that in interval notation, we're going from negative infinity to negative 41, union 39 to infinity. And we have our solution. So with absolute values, it's important to note we're going to have to make a big decision with these absolute values. We're first going to have to isolate the absolute value, get it alone, and then, that's a bad then decide if the absolute value is greater than some number, emphasis on greater than a number, it is an OR inequality with a union. Contrast this with if the absolute value after it's alone is less than some number, less is tripartite, where x is between negative n and positive n. So you're going to have to decide that on each inequality problem. Which one is it? So you can set it up correctly and then solve. Today's homework assignment in 1.8 takes a look at absolute value equations and all types of absolute value inequalities. Practice, practice, practice. Come to class with questions. We will see you then.